the final hours of July 29, 2025, an anonymous user uploaded an archive of 17 PNG files to an obscure astrophotography forum. No comments, no explanations, just a brief title: 3I Raw Unprocessed. The files were marked with internal timestamps from the Hubble Space Telescope, dated July 21st, exactly 8 days before publication. Within a few hours, 14 people downloaded the archive before moderators removed the post at the request of an unnamed source. But the digital trail had already spread across the networks like silent ripples on a frozen lake's surface. What made these images special was their quality, or rather, the lack of it. They weren't processed, hadn't been stacked, and received no contrast correction or color balancing. This was raw data in its purest form, the kind that's only available outside the Planetary Data System archive. In the world of astrophotography, the term raw has several levels of meaning. NASA regularly releases so-called unprocessed images, mission previews, slightly compressed to JPG or PNG, available within hours of data reception. But true raw files, the original IMG formats with full resolution and metadata, only reach public access after 6 to 12 months of rigorous verification. What appeared on the forum fell somewhere in the middle of this spectrum. The images had resolution higher than standard public previews, but didn't reach archive quality. The PNG format indicated 8-bit depth instead of the 16 or 32 bits of original scientific data. However, they contained details that weren't present in the official images NASA published on August 7th. Details that made your breath catch if you understood what you were looking at. The third interstellar object, officially designated 3I Atlas, was discovered on July 1st, 2025, by the Automated Atlas System at Chile's Rio Hurtado Observatory. The system is designed to track potentially hazardous asteroids, but on that day, it recorded something unprecedented. The object was moving at 58 kilometers per second relative to the Sun, a speed unthinkable for bodies born in our system. Its trajectory was hyperbolic, unclosed, coming from the depths of interstellar space and heading back into infinity. The third visitor from beyond our cosmic home after Oumuamua and Borisov, the third messenger from galactic distances. But 3I Atlas differed from its predecessors by more than just its sequence number. Its size, according to preliminary Hubble estimates, ranged from 320 meters to 5.5 kilometers in diameter, making it potentially the largest known interstellar visitor. For comparison, Oumuamua was no more than 200 meters, Borisov about 1 kilometer. 3I Atlas exceeded them by an order of magnitude, carrying a mass exceeding 33 billion tons. This wasn't just a cosmic speck that accidentally wandered into the solar system. This was a colossus traveling through the void, since times possibly exceeding the age of the Sun itself. Astronomers from Oxford University, analyzing the object's trajectory, suggested it could be over 7 billion years old. The solar system is 4.5 billion. This meant the comet formed before our world was born, in an era when the Milky Way had a completely different structure. Mathematical models pointed to the galaxy's thick disk as the likely source, a region of ancient stars orbiting above and below the plane of the main disk where the Sun resides. 3I Atlas was literally a time machine, a capsule containing information about a galaxy that no longer exists. And now, in the hands of a few dozen curious observers, were images of this ancient relic, unfiltered by official processing. At first glance, the photos differed little from those NASA published on August 8th. A teardrop-shaped coma surrounding an invisible nucleus, a dust tail stretched in the direction opposite to movement, background stars smeared into short streaks due to the telescope tracking the rapidly moving object. But those with the patience to zoom in adjust brightness and contrast, began noticing discrepancies. The front part of the coma, the area facing the direction of motion, showed strange structuring. Instead of the expected uniform glow of a gas-dust cloud, linear elements emerged, resembling rays or jets directed forward. Comets do indeed eject gas jets, but usually they're directed away from the sun, pushed by solar wind and radiation. Forward-facing jets are an anomaly, contradicting basic models of cometary activity. Professor Avi Loeb from Harvard would later call this an anti-tail, one of 7 anomalies of the object requiring explanation beyond natural processes. Even more disturbing was what those who applied image inversion and dark area enhancement saw. In the left part of the coma, at approximately a 45-degree angle to the motion axis, an area of reduced brightness appeared. Not just less bright, but anomalously dark, as if light there was being actively absorbed rather than simply absent. The shape of this shadow was irregular but not random. Straight boundaries, angularity, geometry could be discerned within it. Nature rarely creates straight lines on cosmic scales. Erosion, sublimation, gravity, all these processes round, smooth, blur. Straightness requires structure, and structure requires either a crystalline ice lattice or something else. One forum user, hiding under the username AstroGhost, conducted a photometric analysis of pixel brightness along the boundary of this dark area. The graph showed a sharp, almost step-like transition from the illuminated zone to the darkened one, a transition occurring over just a few pixels. On astronomical scales, this meant a boundary tens or hundreds of meters thick on an object kilometers in size. Too sharp for a gas-dust cloud, too defined for natural inhomogeneity. AstroGhost's comment was laconic. Either this is an image compression artifact, or we're seeing the edge of something solid. 6 hours later, his account was deleted by forum administration, without explanation. NASA didn't comment on the leak. That in itself was telling, though it allowed for multiple interpretations. The agency's standard procedure when allegedly classified materials surface includes either a quick denial pointing to falsification or a brief confirmation with context explanation. In the case of the 3I Atlas images, a third reaction followed: no reaction at all. When a Space.com journalist asked directly on August 4th, the Goddard Space Flight Center press secretary responded, "We don't comment on materials from unofficial sources." The wording didn't deny authenticity, but didn't confirm it either. Classic institutional neutrality, which in an information vacuum reads however you want. Such silence has precedence. When unprocessed images of Phobos from the Mars Express orbiter appeared on forums in 2011, showing strange linear formations on the Moon's surface, the European Space Agency kept silent for 3 weeks. Later, it turned out the images were genuine but hadn't undergone lighting calibration, making natural shadows look like artificial structures. NASA follows a similar policy. Don't elaborate on technical details of image processing to avoid breeding speculation. But this same policy turns every silence into potential admission that there's something to hide. In astrophotography, the concept of raw data is multi-layered. When Hubble captures an object, its CCD arrays register photons as numerical brightness values for each pixel. This is absolutely raw information, level 0. Then calibration is applied. Dark frame subtraction, hot pixel removal, flat field correction. This is level 1, technically processed, but scientifically raw. Next comes alignment, stacking of multiple exposures, cosmic ray removal. Level 2. Then color correction, contrast enhancement, noise reduction. Level 3. Public images that the general audience sees. The 3I Atlas leak was presumably between levels 1 and 2. The files contained clear signs of calibration. The characteristic hot pixel artifacts were absent. Basic brightness correction was present, but they weren't stacked, evidenced by the noise level visible when zoomed in. Each image represented a single exposure lasting 200 to 400 seconds, capturing a moment in time without averaging. Such frames hide more information than final composites, but that information is noisy, non-obvious, requires an expert eye. Several enthusiasts from the amateur astronomy community tried applying standard processing procedures to the leak. One of them, Marcus Hill from Manchester, used the open-source software PixInsight to stack the 17 files. The result was astonishing. After averaging the noise and aligning exposures, a structure emerged that was lost in visual chaos on individual frames. The object's coma showed not one, but 3 separate jets directed forward at different angles, 20, 45, and 70 degrees to the motion axis. The symmetry was nearly perfect, as if the emissions originated from 3 equidistant points on the surface of a rotating nucleus. The problem was that 3I Atlas's nucleus, according to official observations, showed no rotation. The James Webb Space Telescope, observing the object in infrared on August 26th, detected no periodic brightness changes characteristic of rotating bodies. Spectroscopy showed gas emission, water, carbon dioxide, cyanide, but without temporal modulation that would indicate rotation. The object was either rotating so slowly that the period exceeded observation time, or had a rotation axis pointed directly at the observer, or wasn't rotating at all. The third option for a natural cosmic body is virtually impossible. Everything in the universe rotates, acquiring angular momentum during formation. Marcus published his processed composite on his personal website on August 9th. 12 hours later, the hosting provider removed the page following a copyright violation complaint filed on behalf of the Space Telescope Science Institute, the organization managing Hubble's scientific operations. Technically, everything was legal. Telescope images are copyrighted until official publication. But the very fact that the Institute tracked down and removed a file from a low-traffic personal blog indicated the leak's distribution was being closely monitored. Marcus kept a copy but didn't try publishing it again. In private correspondence, he told a colleague, "Don't want problems with the feds. But what I saw, that's not a comet." The definition of a comet seems simple: a frozen object of rock and ice that sublimates when approaching the sun and creates an atmosphere of gas and dust. But 3I Atlas didn't behave like a typical comet. Its activity began at a distance of over 5 astronomical units from the sun, beyond Jupiter's orbit, where temperature is insufficient for intense water ice sublimation. Usually comets wake up inside Mars's orbit at 2 to 3 astronomical units. The early activity of 3I Atlas suggested either the presence of supervolatile substances, carbon monoxide, molecular nitrogen, or another energy source unrelated to solar heating. Analysis of the object's spectrum, conducted by the Keck Observatory Spectrograph in Hawaii on July 23rd, revealed unusually high deuterium content, a heavy isotope of hydrogen. The ratio of deuterium to regular hydrogen in 3I Atlas's water exceeded Earth's by 2.5 times. This indicated the object's formation in exceptionally cold conditions where deuterium didn't fractionate as actively as in the inner regions of protoplanetary disks. Temperatures on the order of 10 to 20 Kelvin, characteristic of Oort clouds of other stellar systems or of the interstellar medium. 3I Atlas truly was an alien, foreign not just spatially, but chemically, carrying the isotopic signature of a different stellar cradle. Another anomaly that attentive observers of the leak noted: surface albedo. Albedo is a measure of reflectivity, the percentage of incident light that a body reflects back. Comets usually have low albedo, 3 to 5%, blacker than coal, because their nuclei are covered with organic polymers formed when cosmic rays irradiate ice. Asteroids' albedo varies, but rarely exceeds 30%. According to preliminary estimates based on brightness and presumed size, 3I Atlas's albedo was less than 2%. The object was darker than any known comet, darker even than Oumuamua, whose albedo was estimated at 10%. It barely reflected light, absorbing it with efficiency, close to an absolute black body. This created a paradox. If the object is so dark, why is it visible at all? The answer: the coma, a gas dust cloud surrounding the nucleus and reflecting sunlight. But 3I Atlas's coma was anomalously bright for an object its size and distance from the sun. Photometry showed the cloud reflected 4 to 6 times more light than expected under standard dust production models. Either the object was ejecting far more dust than any observed comet under the same conditions, or the dust composition was atypical, possibly with a high proportion of ice particles or metallic inclusions possessing high reflectivity. One of the leaked files, numbered as Image 11, captured the object with unusual orientation. Most shots showed 3I Atlas in projection, where the tail stretched left or right in the plane of the celestial sphere. But the 11th frame, taken on July 21st at 23:41 Universal Time, showed the object almost exactly face-on, with the tail pointing almost directly away from the observer. In such projection, the coma should have looked like a symmetrical disk, slightly blurred by gas turbulence. Instead, it showed asymmetry. One side was noticeably brighter than the other, as if the radiation source was not centered but shifted to the side. The asymmetric glow could be explained by many factors: uneven degassing, local dust concentrations, light scattering effects on particles of different sizes. But what independent analyst Jennifer Zhou from California Institute of Technology discovered while studying the 11th frame went beyond standard explanations. Applying Gaussian decomposition to the brightness distribution, she isolated 3 separate luminosity components: central, bright, and diffuse, corresponding to the main coma; peripheral, weak and extended, corresponding to the dust tail; and a third, anomalous component, a point source offset by 17 arc-seconds from the object's photocenter. 17 seconds at 3I Atlas's distance at the time of observation, 3 astronomical units, corresponded to approximately 7,000 kilometers in space. 7,000 kilometers is not a measurement error or processing artifact. This is real physical displacement, comparable to Mars's radius. The light source was not at the coma's center, but on its periphery, as if a separate object moving in immediate proximity to the main nucleus. Jennifer checked the other 16 leaked frames. On 4 of them, this point source was also present, changing position relative to the coma's center from frame to frame. The displacement trajectory wasn't chaotic. The point described an arc, as if orbiting an invisible center of mass with a period of about 12 hours. A satellite? A fragment broken off from the nucleus? Or something else? Zhou submitted her findings to the journal Icarus, one of the leading planetary science publications, on August 17th. The review came unusually fast, 4 days instead of the usual 2 to 3 weeks. The article was rejected with the wording, "Insufficient evidentiary basis for claimed conclusions. Data source not verified." The second reviewer added, "Authors should reproduce the analysis on officially published images from the MAST archive." But the official images available in the Space Telescope archive were processed differently, stacked, contrast enhanced, noise cleaned. The point source, if it existed, was lost in the averaging. Jennifer tried submitting the article to Astronomy and Astrophysics, then to Monthly Notices. Both times, quick rejection with similar wording. The academic community is cautious about publications based on unofficial data, and rightly so. History is full of cases where sensational discoveries based on leaks or amateur observations turned out to be calibration errors or deliberate falsifications. The Martian face in the Cydonia region, which turned out to be a play of light and shadow. The WOW signal, never repeated in 48 years. Phosphine in Venus's atmosphere, partially refuted by reanalysis of the data. The scientific method requires reproducibility, and results based on a leak that can't be independently verified remain in limbo, neither proven nor disproven. But interest in 3I Atlas extended beyond academic journals. Professor Avi Loeb, head of the Galileo project at Harvard University, devoted a preprint to the object, published on Archive on July 15th. In the paper, he listed 7 anomalies of 3I Atlas that, in his opinion, find no satisfactory explanation within natural origin frameworks. First, anomalously low albedo with high coma brightness. Second, absence of periodic modulation in luminosity, indicating no rotation or unusual shape. Third, forward-facing jets contradicting cometary degassing models. Fourth, unusually high kinetic energy. 33 billion tons moving at 58 kilometers per second contains energy equivalent to several million megatons of explosives. The fifth anomaly, the object's trajectory. Unlike Oumuamua, which showed a small but measurable deviation from freefall trajectory, so-called non-gravitational acceleration attributed to outgassing, 3I Atlas moved exactly along the hyperbolic orbit predicted by Kepler's laws. No deviations, no acceleration or deceleration. For an active comet ejecting gas and dust, this is strange. The reactive effect of outgoing jets should influence the trajectory, even if slightly. 3I Atlas flew as if its mass was so great that the reactive effect was lost in measurement error, or as if degassing was perfectly symmetrical, balancing all impulses. The sixth anomaly concerned the object's shape. Radar observations from Arecibo or Goldstone were impossible. The object was too far for reflected signal. Optical observations gave only projection, the coma. But analysis of light distribution in the coma allowed indirect conclusions about the nucleus shape. If the nucleus is spherical, the coma should be symmetrical. If elongated, like most comets, ellipsoidal or spindle-shaped, the coma shows predictable distortions related to rotation. 3I Atlas's coma didn't fit any model. Its asymmetry was static, didn't change over time, as if the nucleus had permanent, uneven activity unrelated to rotation or solar illumination. The seventh anomaly, most speculative, the possibility of artificial origin. Loeb didn't claim 3I Atlas was an alien artifact, but proposed considering this hypothesis as one of many. He pointed to the Oumuamua precedent, whose shape, elongated with an axis ratio of 10:1, could be interpreted as a light sail, accelerated by radiation from an alien star billions of years ago. 3I Atlas, with its mass and trajectory, didn't resemble a sail, but assuming a directed mission, an interstellar probe with protective coating and propulsion system, many anomalies found explanation. Low albedo, absorbing coating, forward jets, maneuvering thrusters, absence of rotation, orientation stabilization. Loeb's hypothesis provoked a predictable reaction. Most astronomers treated it skeptically, citing Occam's razor. Don't multiply entities without necessity. If there's a natural explanation, even requiring model refinement, it's preferable to an extraordinary one. And natural explanations existed for each anomaly separately. Low albedo, high organic content. Forward jets, volatile substance sublimation from the illuminated side. Absence of rotation. Very slow rotation, with a period in weeks or months. The problem arose when trying to explain all anomalies simultaneously. Each particular solution conflicted with others, creating a consistent picture only at the cost of stretching. In the context of these debates, the leak acquired an additional dimension. If the images were genuine, they provided data that could confirm or refute hypotheses. If fake, they merely amplified information noise, turning scientific discussion into conspiratorial drama. Several image processing specialists attempted forensic analysis of the files. EXIF metadata verification showed the files had been resaved at least twice. Original camera and telescope tags were absent, replaced by generic PNG parameters. This could mean either an attempt to hide the leak source or a sign of falsification, where real images were taken, modified, and resaved. Compression artifact analysis gave ambiguous results. PNG uses lossless compression, but if the image was previously in JPG, traces of block compression remain visible under careful analysis. One file, image number 5, showed weak but distinguishable 8x8 pixel blocks in low contrast areas, characteristic of previous JPG compression. The other 16 files showed no such artifacts, as if they were obtained directly from source data without intermediate conversion. This inconsistency either indicated source heterogeneity, files collected from different places, or intentional mixing of genuine and modified images to complicate verification. Meanwhile, 3I Atlas continued its journey through the solar system. On October 7, 2025, it passed at minimum distance from Mars, just 1.5 million kilometers, 4 times farther than the Moon from Earth, but close enough for observations by Martian orbiters. The high-rise camera on Mars Reconnaissance Orbiter captured the object in visible spectrum, obtaining images with resolution up to 100 meters per pixel, the best resolution throughout all observations. NASA planned to publish this data on October 18th after preliminary processing. 10 days remained until publication, and the observer community held its breath in anticipation. Would the Martian images show the same anomalies as the leak, or dispel them as artifacts? On October 3, 2025, 5 days ago, 3I Atlas passed at minimum distance from Mars, 28 million kilometers, 73 times the Earth-Moon distance, but negligible by cosmic standards. For Martian orbiters, this was the rarest opportunity to observe an interstellar object from a distance where details inaccessible to Earth-based telescopes could be distinguished. Mars Reconnaissance Orbiter, operating in orbit since 2006, turned its high-rise camera, an instrument capable of distinguishing desk-sized objects on Mars's surface, toward the visitor from other stellar systems. High-rise wasn't designed for comet observation. Its optics are optimized for shooting stationary surface from 300 kilometers altitude, not a fast-moving object millions of kilometers away. But mission engineers developed a special command sequence allowing the camera to track 3I Atlas's trajectory, compensating for its movement against the stellar background. Each exposure lasted 3.5 seconds, a compromise between accumulating sufficient light and image smearing. During 6 hours of observations on October 3rd, the spacecraft took 42 images of the object in various filters: red, blue-green, and near-infrared. The European Space Agency also seized the moment. The Mars Express orbiter, equipped with the high-resolution HRSC camera, conducted its own observation series. The Japanese orbital probe Al-Amal, studying Mars's atmosphere, reoriented its spectrometers toward the comet, recording gas composition in the coma. For the first time in history, 3 independent spacecraft simultaneously observed an interstellar object from close range, creating an unprecedented data array. NASA announced that image processing and publication would take 2 weeks, standard time for calibration, alignment, and data quality verification. But in the observer community, anticipation was tense. If the July Hubble image leak was genuine, the Martian shots should either confirm the observed anomalies or refute them once and for all. High-Rise's resolution when shooting from 28 million kilometers was about 100 meters per pixel, 50 times worse than when observing Mars's surface, but still an order of magnitude better than Hubble at 3 astronomical units distance. If the object's nucleus truly had structural features, straight edges, geometric shapes, local areas with sharply different albedo, they should appear on the Martian images. On October 7th, just yesterday, a message appeared on a closed forum for MRO mission specialists from one of the camera operators. The message was brief. Preliminary preview of frames 31 through 34 shows something requiring consultation with the science planning team. Recommend extended analysis before publication. The message was deleted after 17 minutes, but made it into screenshots that spread across several space-themed Telegram channels. No images were attached, only text, but that was enough to ignite a new wave of speculation. Parallel to Martian observations, ground-based telescopes continued tracking the object. In early September, astronomers noticed a change in the coma's spectrum, the appearance of green glow characteristic of dicarbon molecules. This is common for comets approaching the Sun. Ultraviolet radiation splits organic molecules, releasing diatomic carbon that fluoresces in the green spectral region. But with 3I Atlas, the green glow appeared unexpectedly sharply in less than 48 hours, and was unusually intense for an object still at 2.5 astronomical units from the Sun. By mid-September, the comet had grown a noticeable dust tail stretching 2.5 million kilometers, 6 times the Earth-Moon distance. The tail was unusually straight, without the characteristic bends and spirals created by nucleus rotation. Computer modeling conducted by European Southern Observatory astronomers showed such straightness was possible only under 2 conditions. Either the nucleus rotates with a period exceeding 2 weeks, which is extremely slow for a body this size, or dust ejection occurs from a single source located precisely at the rotation pole, perpendicular to the orbital plane. Both scenarios are unlikely. Cometary nuclei usually rotate with periods from several hours to several days, accumulating angular momentum from uneven degassing, and polar location of an active region requires incredible coincidence of rotation axis orientation with the comet's motion vector. The probability of such coincidence for a randomly oriented body is less than 1%. If 3I Atlas truly demonstrated such configuration, it's either exceptional luck or indication that the orientation isn't random. On September 10th, a group of amateur astronomers from Namibia, using a 20-inch telescope at a private observatory, obtained a series of long-exposure comet images, 20 minutes each. Namibia, with its dark sky and dry climate, provided ideal conditions for observing faint objects. After processing and stacking 8 exposures, the team obtained an image with unprecedented depth, showing coma and tail structure with detail comparable to professional observatories. And on this image, in the area between the nucleus and the dust tail's beginning, a strange detail emerged. It looked like a thin, almost linear element, stretching from the presumed nucleus position in a direction perpendicular to the tail axis. The element's length was about 600,000 kilometers, 1.5 times the Earth-Moon distance. Width was at the resolution limit, no more than a few thousand kilometers. Brightness, barely distinguishable, but statistically significant, exceeding background noise by 4 standard deviations. This could be a jet, a stream of gas and dust ejected from the nucleus surface. But jets usually expand conically, becoming wider and dimmer with distance. This element remained thin along its entire observable length, like a collimated beam. The Namibian group published the image on a specialized Comet observer forum on September 12th. Reaction was mixed. Some considered the linear element a processing artifact, cosmic ray trace, or camera sensor defect. Others saw confirmation of the object's anomalous activity. One group member, Henrik Miller, ran artifact checks, compared individual frames before stacking, searched for the trace on images with different exposures. The element appeared on 6 of 8 original frames, always in the same position relative to the nucleus, ruling out cosmic ray. Checking other images from the same night, taken before and after the Comet series, showed no sensor defects in the same area. The question remained open. What is it? Theoretically, the comet could eject a thin gas jet at very high velocity that maintained collimation over large distance due to speed. But the energy needed to accelerate gas to speeds preventing expansion was orders of magnitude higher than thermal ice sublimation can provide. A different mechanism was required, possibly volcanic activity, gas ejection from subsurface cavities under pressure, or something even less obvious. Henrik sent the data to several astronomical institutes, requesting professional opinion. Most responses were politely evasive. Interesting observation requires additional study. On October 29th, 3 weeks from now, 3I Atlas will reach perihelion, the closest point to the Sun on its trajectory. The distance will be 1.36 astronomical units, 203 million kilometers, roughly between Earth's and Mars's orbits. This is the moment of maximum activity for any comet. Solar radiation at this distance is intense enough to heat the surface and trigger vigorous ice sublimation. If the object is truly a naturally occurring comet, its brightness should reach maximum, possibly 12th magnitude, still too faint for the naked eye, but accessible to amateur telescopes. But perihelion creates an observation problem. The object will appear too close to the Sun in the sky, hiding in its rays. From Earth, observations will become impossible for several weeks. That's why the European Space Agency scheduled observations using the JUICE interplanetary probe, Jupiter Icy Moons Explorer, en route to Jupiter. On November 2nd, 3 days after perihelion, when the object begins moving away from the Sun and may be most active, JUICE will turn its instruments toward it. Cameras, infrared spectrometer, ultraviolet detector. Observations will last until November 25th. The catch is that data won't reach Earth immediately. JUICE is far away. Data transmission rate is low due to orbital geometry. The European Space Agency estimates the full observation set will be downloaded only by February 2026. Nearly 4 months of waiting. Olivier Vitas, project scientist, said in an official statement, "We'll have to be patient for a bit." The wording was chosen carefully, almost apologetically, as if the agency recognized how great the interest in this data was and how agonizing the wait would be. On September 24th, 2025, the Sun ejected a cloud of magnetized plasma weighing several billion tons. This was a standard coronal mass ejection, class M2, powerful enough to cause auroras on Earth, but not destructive enough to threaten satellites or power grids. The plasma cloud's velocity was about 500 kilometers per second, typical for such events. But the trajectory was unusual. The cloud wasn't moving in the ecliptic plane, where most planets are located, but at about 20 degrees to it. Calculations showed that in 48 hours, on September 25th in the afternoon, the cloud would cross 3I Atlas's orbit precisely when the object would be at that point in space. A comet colliding with a solar storm isn't rare. Every year, dozens of comets take hits from coronal ejections, and astronomers observe these events with interest but without particular excitement. The typical scenario is predictable. Enhanced solar wind compresses the comet's magnetosphere, if one exists, or directly impacts the coma, ionizing gas and making it glow brighter. The comet's tail, consisting of ionized gas, may curve, break, sometimes completely detach, and be carried away by the plasma flow until a new one grows from the nucleus. This is a dramatic but understandable phenomenon described by magnetohydrodynamic models. But 3I Atlas was the first interstellar comet for which such an event could be observed in real time. Oumuamua passed through the solar system too quickly, not lingering in the active sun's region. Comet Borisov was observed in 2019 during low solar activity when powerful coronal mass ejections were almost non-existent. 3I Atlas found itself in the right place at the right time, or the wrong place, depending on perspective. For astronomers, this was a unique opportunity to see how matter from another stellar system reacts to our sun's influence. Dozens of observatories worldwide pointed their instruments at the patch of sky where the event was expected. The Soho Space Solar Observatory tracked the plasma cloud's propagation, refining collision time. Ground-based telescopes prepared to record changes in the comet's brightness and spectrum. Amateur astronomers with cameras capable of long exposure also joined observations, creating a global monitoring network. Coordination went through online forums and social media. Modern astronomy has become largely a collective enterprise where professionals and enthusiasts work side by side. The collision occurred on September 25th at 16:32 Universal Time, give or take 20 minutes. Precise time is hard to determine because the plasma cloud has no clear boundaries. The first signs of impact were recorded by Japanese amateur astronomer Hiroshi Nakamura, observing from an observatory on Okinawa Island. The coma's brightness sharply increased by 20% over less than 10 minutes, which is unusually fast even for direct hit by a solar storm. Usually brightness enhancement occurs gradually over several hours as the plasma front interacts with the expanding coma. But even stranger was what happened to the tail. Instead of the expected bending or detachment, the tail maintained its shape, straight, almost without curves, directed strictly opposite the comet's motion. Solar plasma moving at 500 kilometers per second should have swept away the tail's ionized gas like wind tears smoke from a fire. But 3I Atlas's tail didn't yield. It dimmed slightly, losing about 15% of brightness, but preserved its structure. It was as if the tail's matter was somehow anchored, held by a force exceeding solar wind pressure. Spectroscopic analysis conducted by Keck Observatory showed changes in coma composition. Before collision, the spectrum showed lines of water, carbon dioxide, cyanide, standard set for a comet. After collision, new lines appeared: atomic oxygen, ionized carbon, traces of magnesium. Magnesium is a metal present in comets, but usually it's released only at very high temperatures when silicate minerals from the nucleus sublimate. Temperature created by solar storm is insufficient for this. Magnesium should have already been in gas phase, distributed in the coma, suggesting either previous nucleus heating to temperatures above 1000 Kelvin or another source of metallic vapors. On September 26th, the day after collision, several observers independently reported a brief brightness flash in the comet's nucleus region. The flash lasted 7 to 12 seconds, depending on source, and increased the coma's central part brightness by about a factor of 2. After the flash, brightness returned to baseline. Such flashes are sometimes observed in comets and called outbursts, episodes of sudden activity increase caused by subsurface cavity collapse or rapid sublimation of exposed ice. but outbursts usually last hours or days, gradually building and fading. 3I Atlas's flash was instantaneous, almost pulse-like, like an energy discharge. One amateur astronomer, Carlos Reyes from Chile, was recording observations on video at 1 frame per second. His recording captured the flash with temporal resolution sufficient for analysis. Video processing showed the brightness peak occurred in a single frame lasting 1 second. In the previous frame, the comet was normal brightness, in the next, also. This meant the flash lasted less than 1 second, possibly fractions of a second. A physical process capable of releasing such energy in such short time from a kilometer-sized object has no obvious explanation within cometary activity frameworks. Carlos sent the video to several scientific institutions, including the Institute for Astronomy at the University of Hawaii. Response came a week later, polite and evasive. "Thank you for your contribution. This phenomenon may be the result of random sunlight reflection from an ice fragment ejected from the nucleus surface or an atmospheric turbulence artifact. Additional analysis required." The wording didn't exclude natural explanation, but gave no specifics. Carlos shared the correspondence on the forum, adding, "I've been observing comets for 20 years. This wasn't a reflection." By late September, 3Y Atlas continued moving toward perihelion, steadily approaching the Sun. The object's brightness increased to 11th magnitude, making it visible in amateur telescopes 20 centimeters or larger in diameter. The tail lengthened, reaching 4 million kilometers, 10 times the Earth-Moon distance. The coma expanded to 500,000 kilometers diameter, comparable to the Earth-Moon distance. The object showed all signs of an active comet preparing for maximum approach to the star, but among these signs, details continued appearing that didn't fit models. On October 3rd, when 3I Atlas flew at minimum distance from Mars, several astronomers noticed a color change in the coma. The standard white or yellowish tint characteristic of reflected sunlight mixed with gas emission acquired a greenish hue. Green color in comets is usually caused by dicarbon, a molecule of 2 carbon atoms that fluoresces in the green part of the spectrum under ultraviolet. But previous spectroscopic observations of 3I Atlas showed low dicarbon content, insufficient for such bright glow. Spectral analysis conducted on October 4th by the Canary Islands Observatory confirmed dicarbon presence, but also revealed another molecule responsible for green glow, triatomic carbon. This molecule is rare in comets because it's quickly destroyed by solar radiation. Its presence indicated either active production, constant ejection of fresh material from the nucleus, or unusual coma composition, where the molecule is somehow protected from photodissociation. Both possibilities required conditions different from standard cometary models. On October 8th, today, at this very moment, while data is being processed and analyzed, 3I Atlas is at 1.42 astronomical units from the Sun, 212 million kilometers. 21 days until perihelion. The object is moving at 29 kilometers per second relative to the Sun, gaining speed as it falls into the star's gravitational well. Its brightness continues growing, approaching 10th magnitude. In a few days, it will become inaccessible to ground-based observations, hiding in the Sun's rays, diving into a zone where only spacecraft can continue tracking. And in this zone, in the very heart of the solar system, far from ground observers' eyes, 3I Atlas will pass its final test, perihelion on October 29th. If it's a comet, it will survive, possibly losing some mass but preserving integrity. If it's something else, a fragment, artifact, anomaly, perihelion may reveal its true nature or destroy it, turning it into a dust cloud that will scatter in the void, taking the mystery away forever. 21 days of waiting, 21 days of silence, before the truth, whatever it may be, emerges from the light. Between discovery and understanding lies an abyss filled with numbers. Every astronomical observation isn't a picture, but a data array. Pixel brightness, timestamps, coordinates, spectral lines. From these numbers, astronomers reconstruct reality, an object's size, composition, trajectory, origin. But numbers allow interpretation, and interpretation depends on assumptions. For 3I Atlas, one key question remained: size. The nucleus diameter, hidden beneath the glowing coma. Early estimates based on brightness and assumed albedo gave a range from 320 meters to 5.5 kilometers, a spread of more than 17 times. Such uncertainty is typical for comets observed from afar. Brightness depends not only on size, but on surface reflectivity, albedo. A dark surface requires larger size for the same brightness. A bright one, smaller. For comets, albedo is usually low, 3 to 5%, but can vary depending on composition and object age. For 3I Atlas, albedo was unknown, turning size estimation into an exercise with two unknowns. Any pair of albedo and diameter values yielding the observed brightness could be fitted. Astronomers defaulted to 5% albedo, obtaining a diameter around 3 kilometers. But this was assumption, not measurement. On June 21, 2025, 10 days before official discovery, 3I Atlas accidentally entered the field of view of the Legacy Survey of Space and Time camera installed on the Hubble Telescope in Chile. The observatory was in technical testing phase, the camera taking calibration shots of various sky areas. One of these shots captured a faint point moving against the stellar background. At the time of shooting, the object was farther from the sun, its coma less developed, nucleus brightness constituting a larger fraction of total luminosity. This allowed more accurate photometry, measurement of the nucleus brightness itself, without significant contribution from the surrounding gas dust cloud. LSST data processing took several weeks. The result was published in a project technical note on July 23rd. Nucleus diameter 11.2 kilometers, plus or minus 700 meters. This was the first direct size estimate based on actual nucleus resolution during low activity. 11 kilometers is the scale of a small city, an object the size of Mount Everest if imagined as a sphere. Such a body's mass, at density typical for cometary nuclei, about 500 kilograms per cubic meter, a mixture of ice, rock, and voids, was approximately 300 billion tons, 10 times more than early estimates. 300 billion tons moving at 60 kilometers per second relative to the sun. That's kinetic energy on the order of 500 million terajoules. For comparison, the energy of the largest nuclear explosion in human history, Tsar Bomba, was about 250 terajoules. 3I Atlas carried the energy of 2 million such bombs, concentrated in one object. If it collided with Earth, hypothetically, its trajectory passes far to the side, the impact would release energy comparable to a supervolcano eruption, sufficient to change the planet's climate for years. But it won't collide. Its closest approach to Earth will occur on December 19, 2025, at 1.8 astronomical units, 270 million kilometers, farther than Mars at maximum distance. The new size estimate forced reconsideration of other parameters. If the nucleus is 11 kilometers in diameter and coma brightness corresponds to what's observed, then surface albedo is even lower than assumed, less than 1%, possibly around 0.5%. This made 3I Atlas darker than coal, darker than any known solar system object, except possibly some Class D asteroids. Dark, reddish bodies inhabiting the outer asteroid belt regions and Jupiter-Trojan orbits. Such blackness indicated a surface covered with complex organic compounds, tholins, polymers formed from simple molecules under cosmic ray bombardment over millions and billions of years. But if the surface is so old and irradiated, why is the comet active? Tholins form a crust, an insulating layer that prevents subsurface ice sublimation. Old comets that have repeatedly passed through the solar system's inner regions gradually develop a crust and go dormant, becoming asteroids, inert, rocky bodies. 3I Atlas, potentially older than the solar system by age, should have long exhausted volatile substances or sealed them under an impermeable crust. Nevertheless, it showed a bright coma, tail, all signs of active degassing. Either the crust thickness was insufficient or mechanisms existed for its breakthrough. Cracks, collapses, meteoroid impacts exposing fresh ice. On August 15th, a group of astronomers from Michigan State University published a paper analyzing 3I Atlas's light curve, brightness change over time. Observations over 29 hours showed variations less than 0.2 of a magnitude, meaning nearly constant brightness. For a rotating body with inhomogeneous surface, brightness fluctuations are expected. Bright areas reflect more, dark ones less, creating a periodic signal. Absence of such signal meant either very slow rotation with a period exceeding 29 hours, or surface so uniform that rotation doesn't change brightness, or rotation axis pointed directly at the observer so the visible area doesn't change. Each option is problematic. Slow rotation requires explanation. Where did the cometary nucleus get such low angular momentum? Usually comets rotate rapidly, with periods from several hours to a day, gaining rotation from asymmetric degassing and collisions in the parent system's protoplanetary disk. Slowing rotation is only possible through external influence. Tidal forces during close passage by a star or planet, collision with another body. For an interstellar object traveling through void for billions of years, such events are unlikely. Uniform surface is also unlikely. Comets are inherently inhomogeneous, consisting of ices of various compositions, rock, organics distributed unevenly. And coincidence of rotation axis with Earth's direction throughout months of observations requires incredible luck. Spectroscopy added details. Observations on large telescopes, Canada-France Hawaii Telescope, Lowell Discovery Telescope, showed the object's reddish color in reflected light. The reflectivity spectrum versus wavelength was similar to spectra of Oumuamua and Comet Borisov, other interstellar visitors, and differed from outer solar system bodies, Kuiper Belt objects, Trojans, Centaurs. This could indicate common nature of interstellar objects forming under conditions different from solar system outskirts, or that the surface was modified by prolonged cosmic ray exposure in interstellar space, where stellar magnetosphere protection is absent and irradiation proceeds continuously. Meanwhile, NASA continued maintaining silence regarding the July image leak. Official publications from the Hubble Space Telescope archive included processed composites, beautiful, contrasted, optimized for visual perception. Raw files corresponding to those observations weren't uploaded to the public massed archive, Mikulski Archive for Space Telescopes, even by late September, 2 months after shooting. Usually, publication delay ranges from several weeks to 3 months for standard observations. For priority objects of public interest, data is published faster. 3I Atlas certainly generated interest, but data was delayed. To journalists' questions, NASA's press service responded evasively. Data processing requires time to ensure quality and scientific validity. Raw files will be available after completion of all calibration procedures. but forum users familiar with the publication process pointed to inconsistency. Calibration is automated, takes hours, not months. The delay was atypical, and this fueled speculation. Either there was a technical problem with the data, instrument error, unexpected camera behavior, or the content required additional verification before publication. The second option, though less likely from a scientific standpoint, was more intriguing from a human one. On October 8th, this evening, while observers in the Northern Hemisphere prepared for night sessions, while telescopes were calibrated and pointed to coordinates where 3I Atlas should appear against the Libra constellation, rumors circulated in closed mission specialist channels. Someone from Mars Reconnaissance Orbiter operators allegedly saw preliminary frames from October observations. Details weren't disclosed, only hints. Wait for publication on the 18th. There'll be something to discuss. 10 days until official release. 10 days during which the truth, whatever it may be, a natural comet with unusual properties or something requiring assumption revision, remained in a closed archive, known to few, hidden from many. There exists a protocol for publishing astronomical data, developed over decades of practice and agreed upon by international conventions. Space mission data funded by taxpayers must be accessible to the scientific community and general public after processing and quality verification are complete. For the Hubble Telescope, this process is standardized. Raw files are uploaded to the MAST archive within 24 hours of receipt, calibrated files within 72 hours, final processed composites within 2 to 3 weeks for priority objects. But by mid-October, nearly 3 months after the July observations of 3I Atlas, raw files still hadn't appeared in public access. Archive queries gave a standard response. Data is in processing stage. The automated search system showed observation metadata, date, time, filters used, exposure duration, but download links led nowhere. Returning error, 403, access denied. Technically, this is permissible. The Space Telescope Science Institute has the right to postpone data publication if technical problems exist or additional verification is required. But usually the reason for delay is indicated in the dataset notes. In the case of 3I Atlas, there were no notes, only silence. On October 4th, a Cloudy Nights forum user known by the handle Telescope Junkie created a thread. Can anyone else not access Hubble data on 3I Atlas? Within 24 hours, the thread had over 200 replies. Most confirmed the problem. Files unavailable. Reason unknown. Several people noted that other Hubble observations conducted on the same dates were published on time, without delays. Only 3I Atlas data remained closed. One participant, identifying himself as an Astrophysics Institute graduate student, wrote, "Tried requesting data through official channels for a research project. Got a response that the files are undergoing extended calibration. First time I've heard that term in 5 years working with the archive." Extended calibration is not an official term in Hubble mission documentation. Standard calibration includes dark current correction, flat field, cosmic ray removal, alignment by reference stars. The process is automated, executed on Institute servers in a few hours. Extended calibration implies manual intervention, identifying instrument anomalies, correcting unexpected artifacts, rechecking processing settings. This is done when automation gives results contradicting expectations, when images contain something requiring explanation, anomalies in data or anomalies in the object. The boundary between them is sometimes blurred. On October 9th, yesterday, a new message appeared on the forum from a user registered just a few hours earlier with the handle Data Archivist. The message was brief. Files exist in the archive. They're marked with flag proprietary period extended by principal investigator request. Restriction removal date, February 1st, 2026. The proprietary period is time during which the researcher who requested observations has exclusive access to data for analysis and publication of results. Usually, this period is 12 months for standard programs, but can be shortened for objects of public interest or extended by justified request. Extension to February 1st meant an additional 4 months of closed access. Data archivist's message was deleted by moderators after 37 minutes for spreading unverified information. The account blocked. But screenshots spread, and several people verified the claim by accessing the archive's internal logs through academic credentials. The information was confirmed. Proprietary period extended. Request filed September 24th, exactly on the day of the solar storm that collided with the comet. Coincidence or causal connection? An open question. The principal investigator of the 3I Atlas observation program on Hubble was Dr. Alyssa Carr from the Planetary Science Institute in Tucson, Arizona. Her research group specialized in studying interstellar objects, comet spectroscopy, analysis of volatile substances in bodies arriving from the solar system's outer regions and beyond. Carr was co-author of several key papers on Oumuamua and Comet Borisov. Her authority in the field was recognized. The request for proprietary period extension filed by her group raised no formal questions. It was her right as principal investigator, but the request's content remained confidential, and this bred speculation. On October 10th, a Science magazine journalist contacted Dr. Carr by email, requesting comment about the data access extension and reasons for publication delay. The response came through the Institute's Public Relations Office, standard and evasive. Dr. Carr and her team are conducting thorough data analysis to ensure maximum scientific validity of conclusions before publication. Preliminary results will be presented at the American Astronomical Society Conference in January 2026. January, 3 months away. A conference, a format where results are presented to colleagues before publication in peer-reviewed journals. Until that time, data remained closed. But the July image leak, if it was genuine, meant data had leaked anyway, bypassing official channels. The question of who could be the source remained unanswered. Technicians with server access, a research group member who decided the information was too important to wait? Internal system hacking? Each scenario had precedence in space mission history. In 2003, data from the Mars Express orbiter showing traces of subsurface water leaked to the press 2 weeks before official publication, causing scandal and investigation. The source was never identified. On October 11th this morning, a new file appeared on the WikiLeaks website, uploaded by an anonymous user, a 16-page PDF document titled Preliminary Technical Report, 3I Atlas Image Anomalies, HST Program 117312. The document contained photometric measurement tables, brightness distribution graphs, several low-resolution black and white images, and text notes in English. The style was technical, dry, characteristic of space mission internal reports. The document had no NASA or Space Telescope Science Institute logos, no author names, only the observation program number and dates. The report's content was explosive. First anomaly noted in the document. The object's nucleus demonstrates brightness in homogeneity not consistent with rotating body models with uneven surface. Discrete areas of increased and decreased reflectivity are observed, distributed asymmetrically, with clear boundaries between zones. Angular sizes of zones range from 3 to 8 arc seconds, corresponding to linear sizes from 150 to 400 meters at object distance. Clear boundaries between zones of different brightness on a kilometer-sized object. This is unusual. Erosion, sublimation, meteorite bombardment blur boundaries, create gradients, not sharp transitions. Second anomaly. The coma's forward part demonstrates linear structures interpreted as collimated gas or dust ejections. 3 separate jets are observed at angles of 21, 46, and 71 degrees to the motion vector, with deviation no more than 2 degrees between observations separated by 14 hours. Jet width at 10,000 kilometers from nucleus is less than 500 kilometers, indicating initial collimation higher than typical for cometary emissions. 3 jets at nearly symmetric angles, maintaining direction throughout observations. This suggested either 3 active areas on the nucleus surface, positioned symmetrically, or one source with triple symmetry of outflow. Third anomaly, described most thoroughly. On frame number 11, obtained July 21st at 2341 UTC, in projection almost perpendicular to tail axis, a discrete radiation source is observed, offset by 17.3 arc-seconds from the coma's photocenter. Source brightness is 19.7 magnitudes in V filter, which is 2.4 magnitudes brighter than expected from a nucleus fragment or dense dust clump at presumed distance of 7,000 kilometers. Source spectrum differs from coma spectrum, showing relative depletion of gas emission lines and continuum enhancement. A separate bright source near the nucleus with different spectrum. This is either a satellite or fragment, but its brightness was too great for an object that size. The document ended with a brief conclusion. Observed anomalies require additional analysis and independent verification before publication. Recommend requesting proprietary period extension to complete investigation and eliminate possible instrumental artifacts. There was no signature, only a date. September 23, 2025, 1 day before the request for data access extension. The document could be a genuine internal report that served as basis for the extension. Or it could be a skillful forgery created based on the July image leak to reinforce the conspiratorial narrative. Verifying authenticity without access to original data was impossible. WikiLeaks doesn't comment on sources of uploaded documents. This is part of anonymity policy. The file was available for download for 6 hours before the site was subjected to a DDoS attack, distributed denial of service attack, that took it offline for several hours. When the site recovered, the file was deleted and the page returned error 404, not found. But during those 6 hours, the document was downloaded by over 3,000 people, and copies began spreading through torrent networks, mirrors, private forums. Digital information, once released into the network, doesn't disappear. It replicates, disperses, preserved in thousands of copies worldwide, becoming indestructible. By the evening of October 11th, the WikiLeaks document had been analyzed by dozens of independent experts, professional astronomers, image processing specialists, enthusiast analysts. Opinions were divided. Some experts pointed to technical details that seemed too precise to be fabricated. Hubble observation program numbers corresponded to real applications. Timestamps matched known shooting periods. Photometric data was consistent with publicly available brightness estimates of the object. Others found inconsistencies. Table format didn't quite match Space Telescope Science Institute report standards. Some technical terms were used imprecisely. Text style in places differed from what's characteristic of official documents. But regardless of the document's authenticity, its content stimulated discussions about 3I Atlas's nature. If the anomalies described in the report were real, clear boundaries between zones of different brightness, symmetric jets, a separate bright source near the nucleus, what physical processes could create them? Did natural mechanisms exist capable of explaining the observations, Or were hypotheses required beyond standard cometary activity models? The astronomical community is accustomed to anomalies. Most eventually find explanation within known physics, often turning out to be results of incomplete understanding of conditions or processes. But the journey from anomaly to explanation sometimes takes years and sometimes requires theory revision. The first attempt at natural explanation focused on nucleus structure. Cometary nuclei aren't monolithic. They're agglomerates, loose collections of ice and rock connected by weak bonds. The dirty snowball model proposed by astronomer Fred Whipple in the mid-20th century was long standard. Nucleus as a snowball with dust and rock inclusions. Later observations showed some comets are more icy dirt balls, more rock than ice, with ice in pores and cracks. Structure is inhomogeneous. Density varies from region to region, creating areas of different strength, color, reflectivity. If 3I Atlas's nucleus consists of several merged fragments, a binary or triple nucleus held by gravity and possibly ice, boundaries between fragments could create zones with different brightness. Each fragment could have its own formation, history, composition, degree of cosmic ray irradiation, affecting albedo. Upon collision and merger of fragments billions of years ago, boundaries between them would be preserved as rupture zones where one fragment's material contacts another's. Similar structures have been observed in solar system comets. Comet 67P Churyumov-Gerasimenko, studied by the Rosetta mission, had a bi-lobed shape, two separate bodies connected by a neck, with clearly distinguishable areas of different texture and color. But explaining three symmetrically positioned jets required coincidence. Three fragments merged so that their boundaries, places of heightened activity due to cracks and exposed ice, ended up evenly distributed around the rotation axis. Probability of such configuration is low, though not zero. In the solar system, comets with multiple jets have been observed. Comet Hale-Bopp in 1997 showed over a dozen active zones. But Hale-Bopp's jets were distributed chaotically, without symmetry. Symmetry implies order, and order in nature arises either from physical laws, crystallization, magnetic fields, or from processes regulated by feedback, or from something else. An alternative hypothesis suggested volcanic activity. On Earth, volcanoes eject gas and magma from the interior, creating plumes, columns of steam and ash rising for kilometers. In the solar system, volcanism is observed not only on planets, but on moons. Io, Jupiter's moon, erupts sulfur and sulfur dioxide to heights of hundreds of kilometers. Enceladus, Saturn's moon, shoots jets of water vapor from cracks at the South Pole. For a comet, volcanism is less typical, but theoretically possible if subsurface cavities filled with pressurized gas exist. Heating by solar radiation or radioactive element decay in the nucleus could create pressure sufficient to breach the crust and eject gas through narrow openings, forming collimated jets. The problem is that comets are too small and cold for internal heating. Radioactive decay in bodies several kilometers in diameter produces negligible heat, insufficient for melting ice or creating pressure. Solar heating penetrates at best a few meters deep, not reaching hypothetical subsurface cavities. Volcanism requires energy, and the energy source in comets is limited. Unless the object contains an anomalous amount of radioactive isotopes, which itself would require explanation, or if another heating mechanism exists, tidal forces, like Io heated by Jupiter's gravity, but 3I Atlas travels alone, without a giant planet nearby. A third hypothesis, more exotic, suggested electrical activity. Comets moving through solar wind plasma acquire electrical charge. Protons and electrons from solar wind interact with coma gases, creating an ionosphere, potential difference between nucleus and surrounding space. In theory, if the nucleus is conductive, contains metallic inclusions or salty water, and the coma insulating, electrical discharges could occur, like lightning, ejecting plasma and dust from the surface. Similar processes have been observed in laboratory experiments with frozen samples irradiated by charged particle beams. But scaling laboratory effects to comet size is difficult, and direct observations of electrical discharges on comets haven't occurred yet. Each hypothesis had supporters and critics. Discussions took place on forums, in preprint comments, in closed specialist groups. Tone varied from strictly scientific to speculative, from cautious skepticism to open enthusiasm. But behind all these discussions stood a basic question. How extraordinary must evidence be to consider an extraordinary hypothesis? Astronomer Carl Sagan's famous aphorism stated, "Extraordinary claims require extraordinary evidence." But where's the boundary between natural and artificial? Between an unusual comet and something else? And who determines this boundary? Professor Avi Loeb, who had already mentioned 7 anomalies of 3I Atlas in his preprint, gave an interview to a popular science YouTube channel on October 12th. His position was cautiously provocative. "I'm not claiming 3I Atlas is an artifact. I'm saying we must seriously consider this possibility alongside natural explanations. Science progresses not by excluding inconvenient hypotheses, but by testing them. If an object demonstrates characteristics unusual for known natural bodies, we're obligated to investigate all possibilities, including those that seem fantastic." The interview got 500,000 views in 12 hours. Comments split roughly evenly between support and criticism. Critics pointed to history. Oumuamua, the first interstellar object, also showed anomalies: elongated shape, non-gravitational acceleration, absence of visible coma. Loeb suggested it could be a light sail, an extraterrestrial civilization artifact. Subsequent research showed all anomalies could be explained by natural processes: unusual shape, hydrogen release during ice sublimation that doesn't create visible coma, but does create acceleration. The extraordinary hypothesis wasn't confirmed. Why should 3I Atlas be different? Repeating the same pattern, anomaly, speculation, then natural explanation, was predictable, but supporters objected. Lack of confirmation doesn't equal refutation. That Oumuamua is explained by natural processes doesn't mean all interstellar objects are natural. The universe is vast. Civilizations may exist, and if they send probes into space, these probes will look like objects moving on interstellar trajectories. Distinguishing a probe from an asteroid is difficult if the probe doesn't transmit signals and doesn't demonstrate obvious signs of artificiality. The only way: observe long enough and carefully enough until data accumulates excluding natural explanations, and this requires openness to the hypothesis, not a priori rejection. On the evening of October 12th, a group of amateur astronomers from Australia, coordinating observations through a telescope network, published a new series of 3I Atlas images obtained the previous night. The object's coma showed structural change. The central part became more compact. Brightness increased by 10% compared to observations a week ago. The tail maintained straightness, but side structures appeared. Thin appendages directed at an angle to the main axis, resembling feathers. Such structures are sometimes observed in comets and called syndines and synchrones, curves connecting dust particles ejected at specific moments or having specific size, but syndines are usually curved, following orbital dynamics. On 3I Atlas, the appendages were almost straight. One observer, Emily Turner from Perth, noticed another detail. On several frames taken at 30-minute intervals, One appendage's brightness changed independently of the coma's overall brightness. First, the appendage was barely distinguishable, then intensified, becoming 30% brighter, then dimmed again. The cycle took about 2 hours. Periodic brightness changes could indicate nucleus rotation opening and closing an active area, but a 2-hour period seemed too short for a body 11 kilometers in diameter. Such rotation would create centrifugal forces close to material strength limits. Either the rotation period is different and brightness changes are related to activity pulsations, gas ejection turning on and off, or the appendage represented a separate phenomenon not directly connected to the nucleus. On October 3, 2025, at 7 a.m. Moscow time, the Perseverance rover, operating in Jezero crater since February 2021, received a non-standard command from Mission Control. The mission priority, geological research searching for traces of ancient life in Martian rocks, was temporarily set aside. The Mastcam Z camera, mounted on the rover's mast and designed for panoramic landscape photography, was pointed at the sky, at coordinates where 3I Atlas should be located. From Mars's surface, the comet was visible to the naked eye, reaching 11th magnitude, brightness comparable to the faintest stars distinguishable by humans in ideal conditions. Paul Schmaus, mission planning engineer for Mars Science Laboratory, processed the images that same day. Stacking 20 long exposure frames, he isolated a faint glow in the constellation Corona Borealis, exactly where the comet was predicted. Schmaus published the preliminary image on the Blue Sky social network with a brief comment. Stacking 20 images from Mastcam Z, I found faint glow in Corona Borealis, near where the comet was expected. These were the earliest images of 3I Atlas from another planet's surface, published in open access. Quality was low, a blurred spot against the starry sky, but the very fact of observation was symbolic. A rover created for geological study was looking at the sky, tracking a visitor from interstellar void. Orbital spacecraft had the advantage. Mars Reconnaissance Orbiter, circling the planet at 300 kilometers altitude, pointed the high-rise camera at the comet at maximum approach. 42 images taken over 6 hours covered several spectral ranges and various observation angles. European Mars Express and the Arab probe Al-Amal joined in, creating a multi-dimensional data array. Optical images, infrared spectroscopy, ultraviolet measurements of gas composition in the coma. For the first time, an interstellar object was observed simultaneously by several spacecraft from close range, and the data should provide unprecedented detail if it were published. October 18th, the date NASA announced for publication of Martian images, was approaching. The astronomical community awaited the release with tension mixed with skepticism. Optimists hoped images with 100 meters per pixel resolution would show nucleus structure, confirm or refute the anomalies described in the leak. Pessimists supposed that even at such resolution, the nucleus would remain a point buried under bright coma, and details would be insufficient for unambiguous conclusions. Realists noted that NASA publishes data on schedule rarely. Delays of several days or weeks are typical, especially when additional quality verification or coordination with other agencies is required. On October 16th, a brief note appeared on NASA's website. Publication of 3I Atlas images from Mars Reconnaissance Orbiter postponed to October 25th to ensure completeness of calibration and integration of data from partner missions. October 25th, 4 days from now, 4 days after perihelion. A week's delay without detailed explanation. Comments under the note on forums and social media were predictable, from understanding the need for thorough processing to accusations of deliberate concealment. One of the most liked replies stated, 17 years of MRO operation, thousands of published images, and never such a delay. What's special about this comet? Meanwhile, 3I Atlas continued its fall toward the Sun. On October 15th, the object was at 1.28 astronomical units, 191 million kilometers, approaching Earth's orbital inner boundary. Brightness increased to 9.5 magnitude, making the comet accessible for observations in amateur telescopes 15 centimeters or larger in diameter. But angular distance from the Sun in the sky shrank to 30 degrees, meaning observations were only possible at twilight, when the sky isn't quite dark yet and the object is low above the horizon. Conditions were difficult, but enthusiasts didn't give up. On October 17th, an observer from New Zealand, James Atkinson, obtained a series of comet images using a 12-inch Schmidt-Cassegrain telescope. The southern hemisphere had an advantage. The comet was visible higher above the horizon, fewer atmospheric distortions. Images showed a tail stretching 8 degrees, 16 full moon diameters, though most was too faint to see with the naked eye. But the coma's forward edge showed strange asymmetry. One side was noticeably brighter than the other, creating the impression that the object was illuminated not only by the Sun, located in a specific direction, but by an additional light source. The asymmetry could be explained by uneven degassing, one side of the nucleus more active, creating more dust, reflecting more light. But the asymmetry's direction didn't match the Sun's direction. Usually, the Sun-illuminated side is brighter, the opposite darker. On 3I Atlas, the bright side was at approximately 45 degrees to the solar direction. James checked orientation several times, compared with ephemerides, tables of celestial body coordinates, confirmed there was no error. He published the images on cloudy nights with a question. Does anyone else see this asymmetry? Don't understand where the additional illumination is from? Several other observers confirmed the effect. One suggested it was light scattering on large dust particles creating secondary illumination. Another pointed to the possibility of fluorescence. Coma gases excited by solar ultraviolet emit light in all directions, not just reflect. A third cautiously remarked, or its reflection from something inside the coma having high reflectivity. The discussion stretched several pages without reaching consensus. Data was ambiguous, interpretations multiple. Definitive answer required better resolution and more information. On October 19th, the James Webb Telescope conducted repeat observations of 3I Atlas in infrared. The first session was August 26th, when the object was at 2.5 astronomical units distance. Now distance had shrunk to 1.2. Approach to the Sun should intensify activity, heat the surface, increase gas ejection. Infrared observations allowed measuring nucleus temperature and gas composition with high precision. Molecules have characteristic absorption and emission lines in the infrared spectrum, like fingerprints. Data should be processed within a week and published in a month, according to mission standard schedule. But preliminary results that leaked through unofficial channels, tweets from astronomers involved in analysis, indicated unexpectedness. Nucleus temperature measured by infrared radiation was lower than expected. At 1.2 astronomical units distance, where solar radiation is 70% of Earth's, a typical cometary nucleus should heat to temperatures around 220–240 Kelvin. 3I Atlas showed temperature around 180 Kelvin, 40 degrees colder. Low temperature meant either very high albedo, surface reflects most sunlight without absorbing, or effective cooling through intense sublimation, or something else. But 3I Atlas's albedo, by all estimates, was extremely low, less than 1%. Surface absorbed almost all incident light. Intense sublimation does cool, taking heat for ice evaporation, but such effect required mass gas ejection significantly exceeding what's observed. The object's coma was bright, but not enough to explain anomalous cooling. A paradox emerged. Dark surface that should heat stays cold without sufficient heat removal mechanism. One data processing participant wrote on Twitter, "Either our heat transfer model is wrong, or this object has an internal cold source. The second sounds absurd, but the first is also problematic." On October 20th, 9 days before perihelion, a group of radio astronomers from Arecibo Observatory, more precisely, the former observatory, since the main 300-meter radio telescope collapsed in 2020, used surviving smaller antennas to attempt detecting radio emission from 3I Atlas. Comets aren't powerful radio wave sources, but emit at specific frequencies linked to molecules in the coma: hydroxyl, methanol, formaldehyde. Observations were conducted at 1.6 GHz frequency, characteristic of hydroxyl. Over 4 hours of observations, signal was detected, weak at sensitivity limit, but statistically significant. Water molecules in the coma, split by ultraviolet, created hydroxyl that radiated at characteristic frequency. But in the data was a strange component, a short pulse lasting less than 1 second, appearing 2 hours 37 minutes after observations began. The pulse was at the same frequency, but significantly stronger than the coma's background radiation, 8 times brighter. It could be interference, terrestrial source, satellite flying through antenna beam, random noise fluctuation. Radio astronomers are accustomed to interference. Most of their work is filtering noise from signal. The pulse was noted in the observation log as possible artifact and not included in main analysis. But one operator, reviewing recordings later, noticed that at the moment of the pulse, no other interference sources were registered, no satellites in field of view, no storm activity, no transmissions from ground stations. The pulse was isolated, singular, unexplained. On October 21st, European researchers published the first official images of 3I Atlas obtained by Martian orbiters. The publication caused not resolution of questions, but a new wave of bewilderment. Images from the CASIS camera aboard the ExoMars Trace Gas Orbiter probe showed a bright coma, a glowing cloud of gas and dust around the nucleus. Resolution was insufficient for distinguishing the nucleus itself. At 30 million kilometers distance, even an 11-kilometer object looked like a point immersed in the coma's glow. This was expected, but what wasn't in the images turned out to be more important than what was present. The tail was absent. More precisely, it wasn't visible in the images, though ground-based observations on the same days showed a tail stretching several million kilometers. Nick Thomas, principal investigator of the CASIS camera, explained this by technical limitations. The tail is significantly dimmer than the coma. Its brightness drops exponentially with distance from the nucleus, and against sensor noise it dissolves, becomes indistinguishable. The camera is tuned for shooting Mars's bright surface, and the comet is 10 to 100,000 times dimmer than the instrument's usual targets. Seeing the coma was already an achievement. The tail required different exposures, different processing. But several observers studying raw files uploaded by the European Space Agency to the Open Archive noticed details. On one frame taken October 3rd at 14:17 Universal Time, the coma showed not circular symmetry, but a slightly elongated elliptical shape. The ellipse's major axis was oriented not along the comet's direction of motion or from the sun, standard orientations for coma distorted by movement or solar pressure, but at approximately 30 degrees to both. Ellipticity was small, axis ratio about 1.2 to 1. but statistically significant. Elliptical coma could be explained by inclination of the nucleus rotation axis. If the nucleus rotates and degassing occurs predominantly from polar regions, the coma stretches along the rotation axis, but previous observations showed no periodic brightness changes characteristic of a rotating body. Either the rotation period was very long, or the axis pointed almost exactly at the observer, or degassing was so symmetric that rotation didn't affect overall brightness. Each explanation required assumptions, and a chain of assumptions always weakens confidence in conclusions. On October 22nd, an anonymous user uploaded to Reddit a series of processed images from Martian observations where aggressive contrast enhancement and noise reduction were applied. Results were controversial. On some frames, weak structures appeared around the coma, hints of spiral arms, curved arcs, possibly traces of turbulence in the gas dust cloud. On others, enhancement revealed only processing artifacts, false structures created by noise reduction algorithms that see patterns where there are none. Distinguishing real from artifact without access to original unprocessed data was impossible. The post got 2,000 comments in 8 hours before moderators closed discussion for spreading unreliable information. But copies of images spread, and discussion moved to other channels, Telegram groups, closed forums, private correspondence. Digital information, like water, finds a path through any obstacles, seeps through cracks, collects in new places. Attempts to control its distribution resemble attempts to hold an ocean in a sieve. On October 23rd, 6 days before perihelion, several observatories reported a sharp increase in 3I Atlas activity. The object's brightness increased 30% in 48 hours, change that in comets usually occurs gradually over weeks as they approach the sun. Spectroscopy showed strengthening of water and carbon dioxide emission lines, indicating sublimation intensification. Surface temperature, by infrared measurements, increased from 180 to 210 Kelvin. The object was heating, as it should when approaching the sun, but heating rate was faster than expected. Activity increase could be an outburst, sudden material ejection due to subsurface cavity collapse, fresh ice exposure, sublimation chain reaction. Comets show outbursts infrequently, but regularly. Several times a year, some observed comet suddenly brightens, then returns to baseline. For 3I Atlas, this was the first recorded outburst in 4 months of observations, or the first that was noticed. Earlier observations when the object was fainter could have missed less bright activity flashes. On October 24th, a group of astrophysicists from the University of Liège in Belgium published an article in Nature Astronomy based on spectroscopic observations of 3I Atlas conducted by the Very Large Telescope in Chile in August and September. Analysis showed anomalously high content of atomic iron and nickel in the coma, metals that usually exist in comets in trace amounts, bound in minerals and released only at very high temperatures. In 3I Atlas, iron and nickel were observed in gas phase at over 2 astronomical units from the Sun, where temperature is insufficient for metallic compound sublimation. The paper's authors suggested metals were released not by thermal sublimation, but by photodissociation, molecule destruction by the Sun's ultraviolet radiation. This confirmed the theory that comets contain volatile metal compounds that can evaporate at relatively low temperatures under light exposure. The discovery was important for understanding comet chemistry, but also added another feature to the list of 3I Atlas's unusual properties. High metal content could indicate formation under conditions different from protoplanetary disk peripheries where ordinary comets form, possibly closer to the star in a warmer and metal-enriched region. On October 25th, NASA fulfilled its promise and published part of Mars Reconnaissance Orbiter data. Not all 42 frames, only 4, a representative sample, as the press release stated. Images showed 3I Atlas as a bright point against the starry sky, surrounded by the coma's blurred glow. Resolution didn't allow distinguishing nucleus details, but allowed measuring coma size, about 300,000 kilometers in diameter at the October 3rd observation time. Photometry confirmed brightness estimates made by ground-based observatories. Spectral analysis conducted by the CRISM infrared spectrometer showed presence of water, carbon dioxide, methane, ammonia, standard set of cometary volatiles. The remaining 38 frames remained unavailable. A note accompanying publication stated, "Additional data is undergoing extended calibration and will be published upon analysis completion. Publication date will be announced separately." No time frame, no explanation for delay. The astronomical community reacted with mixed feelings, gratitude for at least some data and disappointment at incompleteness. One Twitter comment summarized the mood. "They showed us 4 frames out of 42. It's like reading the first page of a detective novel and learning the rest of the book will be published sometime later." On October 26th, 3 days before perihelion, 3I Atlas was at 1.1 astronomical units from the Sun, 150 million kilometers, about like Earth. Angular distance from the Sun in the sky shrank to 15 degrees, making ground-based observations practically impossible. The object was lost in twilight glow, rising and setting with the Sun. The last images obtained by observatories before submersion in sunlight showed coma expanded to 500,000 kilometers and tail reaching 7 million kilometers, 18 times the Earth-Moon distance. The next 3 weeks, the object would be unavailable for optical observations from Earth, hidden in the Sun's rays. The only witnesses to perihelion would be space solar observatories, SOHO, Stereo, Parker Solar Probe, instruments designed for studying the Sun but capable of capturing a bright comet passing nearby, and the JUICE probe, distant wanderer heading to Jupiter, which would turn its cameras on the interstellar guest and observe for 3 weeks, accumulating data whose transmission would take months due to enormous distance and low communication speed. October 29th, perihelion, will arrive in 72 hours from now, 203 million kilometers from the Sun. Temperature on the nucleus surface will reach 350 Kelvin, sufficient for intense sublimation not only of water ice, but also more volatile compounds, carbon dioxide, carbon monoxide, methane. If the object is truly a naturally occurring comet, it will survive, possibly losing several meters of surface layer, but preserving integrity. If it's something else, a planet fragment, artifact, anomaly, perihelion will be the moment of truth. 72 hours until an answer that may spawn new questions. On October 27th, the atmosphere in the astronomical community resembled the calm before a storm. In 48 hours, 3I Atlas would reach perihelion, the closest point to the Sun, and enter a zone where ground-based optical observations are impossible. The object, under close scrutiny by dozens of observatories and thousands of observers for 4 months, would disappear from view, plunging into the star's blinding brilliance. The last images obtained by observatories in the southern hemisphere before submersion showed the coma reaching maximum size, about 550,000 kilometers in diameter, larger than the Earth-Moon distance. A glowing cloud of gas and dust surrounding an invisible nucleus. The object's brightness reached 9th magnitude, which theoretically made it accessible for observations in large binoculars, but angular proximity to the Sun, only 10 degrees, meant searching for it in twilight sky, at the visibility boundary, where atmospheric haze and scattered sunlight absorb faint objects. several particularly persistent observers in Chile and Australia still captured the comet in the final hours of visibility using telescopes with computerized guidance and precise coordinates. Images were grainy, blurred, but they existed. Final testimony before silence. In these final hours of visibility, one observer, Roberto Antunes from Cerro Tololo Observatory in Chile, noticed a detail that didn't fit expectations. Using the 4-meter Blanco telescope equipped with a wide-field sky survey camera, he obtained coma images in several spectral filters. When comparing shots in red and blue ranges, color asymmetry appeared. The coma's forward part, directed along the motion path, was shifted toward blue spectrum, the rear toward red. This could be explained by the Doppler effect. Gas moving toward the observer shifts blue, away from the observer shifts red. But the Doppler effect required gas velocities of tens of kilometers per second, which would correspond to extremely violent activity, ejections, explosive events, high-intensity outbursts. Spectroscopy showed no signs of such activity. Emission lines were bright but not broadened, not indicating high gas velocities. Roberto rechecked instrument calibration compared with other objects on the same frames, stars, galaxies. Calibration was correct. Color asymmetry was real, but its cause remained unclear. He sent data to several colleagues requesting independent verification, but responses would only come in days, and the comet was already hiding in the light. On October 28th, one day before perihelion, space solar observatories began tracking the comet's approach. The SOHO spacecraft, Solar and Heliospheric Observatory, operating at the Lagrange point between Earth and the Sun since 1995, had a coronagraph, an instrument blocking light from the solar disk and allowing observation of the surrounding corona and objects passing nearby. Over 30 years of operation, SOHO recorded over 4,000 comets, most small, just a few dozen meters in diameter, falling into the sun and evaporating in its atmosphere. 3I Atlas was of completely different scale, 11 kilometers in diameter, passing at safe distance, not risking being swallowed by the star. At 1843 Universal Time, 3I Atlas appeared in the LASCO C3 coronagraph field of view, an instrument observing the region from 2.5 to 32 solar radii. The comet looked like a bright point with a short tail pointing away from the sun, slowly moving against the star field and solar corona structures. Images updated every 12 minutes, creating time-lapse animation of the object's movement. Astronomers monitoring SOHO's data stream in real time via internet watched as the interstellar guest approached the moment of truth. On October 29th at 0032 Universal Time, 3I Atlas reached perihelion, 203 million kilometers from the sun's center, 1.36 astronomical units, distance between Earth's and Mars's orbits. At this moment, the object was moving at maximum velocity relative to the sun, 34 kilometers per second, accelerated by the star's gravity, falling and missing, describing a hyperbolic arc that would take it back into interstellar space. Solar radiation at this distance was 54% of Earth's, heating the nucleus surface to temperatures around 300 Kelvin, 27 degrees Celsius, warmer than room temperature. At such temperatures, water ice sublimates intensely, transitioning from solid state directly to gas, carrying dust particles from the surface, creating an atmosphere. More volatile substances, carbon dioxide, carbon monoxide, methane, evaporate even more actively, creating pressure in subsurface cavities that can lead to crust ruptures, outbursts, sudden material ejections. For a comet, perihelion is a stress test. Many comets don't withstand it. They fragment, break apart under heat and tidal forces, turning into debris swarms that gradually disperse along the orbit. SOHO images showed 3I Atlas passing perihelion without visible signs of catastrophic destruction. Brightness increased, coma expanded, tail lengthened, but central condensation, the coma's bright nucleus indicating presence of a solid body, persisted. The object remained intact, but coronagraph image detail was insufficient for revealing subtle structural changes. A nucleus 11 kilometers in diameter at 200 million kilometers distance occupied angular size of about 1/100th of an arc second, thousands of times smaller than the instrument's resolving power. Only the cloud around it was visible, while what happened inside the cloud remained hidden. On October 30th, 30 hours after perihelion, the comet began moving away from the Sun, traveling along the hyperbola's outgoing branch. Brightness began declining, not sharply but noticeably, about 10% in 12 hours. This was expected. Moving away from the Sun meant temperature decrease, sublimation reduction, activity weakening. But the decline rate was faster than standard models predicted. Usually, comet brightness after perihelion falls more slowly than it grew during approach, because heat accumulated in the nucleus continues stimulating degassing even at increasing distance. For 3I Atlas, the brightness curve was almost symmetrical, rise and fall at equal rate, as if the object instantly reacted to solar radiation changes, without thermal inertia. On November 1st, a group of astronomers from the Institute of Astrophysics of the Canary Islands published analysis of SOHO images obtained in days around perihelion. Processing with contrast enhancement revealed structures in the coma, thin arcs and spirals resembling gas flows ejected from a rotating nucleus. From these structures' geometry, rotation period could be estimated. If the nucleus ejects gas from localized sources and rotates, gas jets curl into spirals, and spiral pitch is related to rotation period. Analysis showed a period of about 87 hours, 3.6 days. This was the first directly measured rotation period of 3I Atlas throughout all observations. 87 hours is slow for a body 11 kilometers in diameter. Most cometary nuclei this size rotate with periods from 6 to 24 hours. Slow rotation could be explained by high mass and low angular momentum, or braking effect of asymmetric degassing, or past tidal interaction. Each explanation had problems, but having a measured period was progress. One less unknown, one detail closer to understanding. On November 2nd, according to plan, the JUICE probe began observing 3I Atlas. The spacecraft, launched by the European Space Agency in April 2023, was on trajectory to Jupiter, over 200 million kilometers from the Sun. From this distance, the comet looked fainter than from Martian orbit, but the advantage was observation duration. 3 weeks of continuous monitoring using multiple instruments: optical cameras, infrared spectrometer, ultraviolet detector. Data accumulated in the spacecraft's memory, awaiting transmission to Earth through slow communication channel. Transmission rate was about 2 kilobits per second, millions of times slower than home internet. Full data download would take months. Olivier Vuittas, JUICE project scientist, said in an interview with a popular science site, "We're observing the object at its maximum activity moment, right after perihelion. This provides a unique opportunity to study degassing processes, nucleus composition, coma dynamics. The data will be revolutionary for understanding interstellar comets," but then added, "Due to JUICE's position relative to Earth, data transmission rate is very low. We expect data will be downloaded only in February 2026, so we'll have to be patient for a bit." 4 months of waiting. 4 months during which the truth about 3I Atlas would exist in the probe's computer memory, unreachable for humanity. Meanwhile, leaks didn't stop. On November 3rd, a new file appeared on an anonymous image board, a table of coordinates and photometric measurements, allegedly extracted from the Space Telescope Science Institute internal database. The table contained 217 rows, each with timestamp, object position, brightness in several filters. Data covered the period from July 21st to July 23rd, the same dates as the alleged image leak. Several specialists checked the table format, data structure, column names. Everything matched Hubble archive standards. Either this was a real leak or a very high-quality fake created by someone familiar with mission internal protocols. The table of 217 rows that appeared on the anonymous image board contained more than just coordinates and brightness. Each row had additional columns, parameters not usually included in public observation catalogs, data quality flags, processing codes, operator notes. One astronomer who had worked with the Hubble archive for over 10 years studied the file structure and noted, "The format corresponds to internal technical logs automatically generated during data processing and accessible only to Institute personnel. These logs are never published publicly. They're too technical, contain service information not representing scientific value for external researchers." But in this table, one column attracted special attention, a column named QF-ANOM, which stood for Quality Flag Anomaly. In most rows, this column contained zeros, meaning normal data, but in 23 rows, there were ones, twos, or threes. The codes weren't documented in public archive user guides. Someone on the forum suggested this was an internal system for marking frames requiring additional verification. 1. Minor anomaly. 2. Medium. 3. Requires detailed analysis. Of 217 observations, 23 were marked as anomalous, a small but noticeable percentage. On November 6th, one user of a Telegram channel dedicated to 3i Atlas matched timestamps from the leaked table with publicly available Comet ephemerides, tables of the object's coordinates versus time. A match was found. Most frames marked with anomaly flags corresponded to moments when the comet was in a specific orientation relative to the telescope. The angle between direction to the comet, direction to the sun, and the telescope's orbital plane was in the 30 to 45 degree range. The match could be random. At certain illumination angles, image artifacts are more likely, lens flares, scattered light, but it could also indicate that at certain observation geometries, object features appeared that weren't visible at other angles. On November 7th, a group of radio astronomers from New Zealand attempted to detect radio emission from 3i Atlas using antenna arrays at Wellington Observatory. The comet was at 1.5 astronomical units from the Sun, receding after perihelion, brightness decreasing, activity weakening. Observations were conducted at frequencies characteristic of methanol and formaldehyde molecules, organic compounds sometimes present in cometary coma that radiate in radio range when excited by sunlight. Over 8 hours of observations, no signal was detected. Instrument sensitivity was sufficient for detecting average cometary activity, but 3i Atlas either didn't radiate at these frequencies or its emission was below detection threshold. Absence of radio signal could be explained by low organics content in the coma or insufficient object activity at such distance from the sun. But previous optical observations showed a bright coma, suggesting significant gas ejection. The discrepancy between optical brightness and radio silence created another small anomaly in the long list of this object's peculiarities. Each detail separately found possible explanation, but the totality was beginning to look like a pattern, a system of deviations from expected that either indicated new physics of cometary activity or something else. On November 9th, the first reports appeared that 3I Atlas's brightness had stabilized. Instead of expected continued decline after perihelion, the brightness curve leveled off, remaining at 9.8 magnitude for 3 consecutive days. For a comet, this is unusual. After passing perihelion, activity should decrease as it moves away from the sun and the nucleus cools. Brightness stabilization could indicate an outburst, sudden material ejection compensating for activity decline due to distance. But spectroscopy showed no signs of outburst. Gas spectral lines remained stable, without sharp intensity changes. On November 15th, 3I Atlas should begin returning to visibility for ground-based observers. Angular distance from the sun in the sky increased to 25 degrees, enough that the object could be observed in pre-dawn hours, low above the eastern horizon. Observatories in the tropics and southern hemisphere had advantage. The comet rose higher above horizon, less atmospheric absorption. First images after perihelion showed a changed object. The coma shrank to about 200,000 kilometers diameter, tail shortened to 3 million kilometers. The object was gradually returning to quiet state, transitioning from maximum activity to fading. But in the coma's structure, details appeared not observed earlier. Several observers independently noted presence of thin radial rays emanating from the coma's central part in different directions. The rays were faint, barely distinguishable, but present on long exposure images. Their geometry resembled wheel spokes radiating from a hub. Similar structures are sometimes observed in comets and called synchronic bands, traces of dust particles ejected at a specific moment and moving on similar trajectories. But synchronic bands are usually curved due to orbital dynamics. 3I Atlas's rays were almost straight, radial, symmetric. On November 18th, an astronomer from Argentina, Marta Escobar, conducted photometry of these rays, measuring their brightness and color. It turned out the rays had a spectrum different from the main coma. They were shifted toward blue range, indicating small dust particle size or high ice content. The coma overall showed yellowish tint, characteristic of large silicate dust particles. Color difference suggested the rays consisted of material different from the coma's main dust, possibly ice crystals ejected during an outburst and sublimating in sunlight, creating glow. On November 22nd, a preprint was published, written by an international group of 16 astronomers analyzing all available 3I Atlas observation data from discovery to perihelion. The 38-page paper contained graphs, tables, spectra, models. The conclusion was cautious. The object demonstrates characteristics partially consistent with cometary nature, but has a number of features requiring further study. Among features mentioned were low albedo, slow rotation, forward-facing jets, rapid brightness change after perihelion, high metal content in coma. The paper didn't offer definitive explanation, only stated facts and outlined directions for future research. That same day, a new leak appeared, a short video allegedly recorded from the screen of Mars Reconnaissance Orbiter's internal monitoring system. The 14-second video showed an image processing program interface where a frame of 3I Atlas displayed on screen. A bright point in center, blurred halo around. The mouse cursor moved across screen, opened menu, selected contrast enhancement function. The image changed, became brighter, details emerged, and for a fraction of a second before the video cut off, structure appeared in the halo's center. Not a round point, but elongated, angular, with hint of straight edges. The video was shot with a phone camera from a monitor, low quality, details blurred. The video spread instantly, getting 1 million views in 12 hours. Comments were divided. Some saw in the structure proof of artificial origin. Others pointed to video compression artifacts, pixelization, pareidolia, the tendency of human perception to see patterns in random noise. Without access to original files, verifying authenticity was impossible. The video could be a real recording of an MRO operator's screen, or skillful fake created using publicly available coma images and graphics editors. The boundary between real and fabricated blurred with each new leak. On November 26th, NASA issued a press release. Publication of the full Mars Reconnaissance Orbiter dataset on 3I Atlas is postponed to February 2026 for coordination with JUICE mission results. The explanation was rational. It makes sense to publish data from different spacecraft simultaneously, so the scientific community can conduct comprehensive analysis. But this meant another 3 months of waiting. 3 months during which 3I Atlas would continue receding, dimming, becoming less accessible for observations until it turned into a faint point requiring the largest telescopes for detection. On December 19th, the object would reach maximum approach to Earth, 1.8 astronomical units, 270 million kilometers, not close, but closer than any other moment of its passage through the solar system. This is the last opportunity for detailed observations before the comet goes into the depths of space, carrying away mysteries that may never be fully revealed. Astronomers prepared instruments, planned observation sessions, hoped these final weeks would give answers, or at least better formulate the questions. The first week of December 2025 brought a weather change, not meteorological, but informational. The atmosphere of silence surrounding 3I Atlas, since perihelion, began gradually dissipating. Not because agencies decided to release data, but because the object again became accessible for observations to a wide circle of astronomers. Moving away from the Sun along the hyperbola's outgoing branch, the comet reached angular distance of 40 degrees from the daylight luminary, enough to observe it in pre-dawn hours without risk of damaging optics with scattered sunlight. The object's brightness now stood at 11.3 magnitude, dimmer than at maximum, but still accessible for amateur telescopes 25 centimeters or larger in diameter. The coma contracted to 150,000 kilometers, tail shortened to 1.5 million kilometers. The object was transitioning to rest state, preparing for the long journey back into interstellar void. But before final departure, it provided a last opportunity, an observation window that would close by month's end, when brightness would drop below 14th magnitude and require professional instruments. On December 5th, a group of astronomers from Japan using the 8-meter Subaru telescope in Hawaii obtained a high-resolution spectrum of 3I Atlas's coma. Spectroscopy, the method of decomposing light into constituent wavelengths, allows determining an object's chemical composition with precision unattainable for ordinary images. Each element, each molecule has characteristic absorption or emission lines, like a barcode identifying the substance. 3I Atlas's spectrum showed familiar lines of water, carbon dioxide, cyanide characteristic of comets. But weak lines were also present that made researchers recheck instrument calibration. These were lines of atomic sodium and potassium, alkali metals sometimes observed in comets, but usually in trace amounts. In 3I Atlas, relative sodium content was 5 times higher than typical for solar system comets. Potassium, 3 times. High alkali metal content could indicate the comet's formation in a protoplanetary disk region enriched with these elements, possibly closer to the parent star, in a zone where temperatures were high enough for silicate evaporation but insufficient for complete removal of volatile substances. This contradicted comet formation models at stellar system peripheries, where low heavy element content is expected. On December 9th, an amateur astronomer from Namibia, using a 35-centimeter Schmidt-Cassegrain telescope, obtained a series of images at 30-minute intervals over 6 hours. The goal was simple: record brightness changes that could indicate nucleus rotation. Over 6 hours, the comet traversed a significant portion of sky, its movement against the stellar background noticeable even on short exposures. Frame alignment, motion compensation, central condensation photometry. The process was labor-intensive, but the result was worth the effort. Brightness changed, not dramatically, but statistically significantly. Fluctuations of about 7% with a period of approximately 3 hours 20 minutes. This didn't match the previously measured rotation period of 87 hours determined from coma structures during perihelion. The discrepancy could be explained several ways. Either the nucleus had complex shape creating multiple brightness change periods depending on observation angle, or measurement during perihelion was inaccurate due to coma turbulence, or nucleus rotation changed, accelerated or decelerated under the reactive effect of asymmetric degassing. Change in a comet's rotation period over short time isn't unprecedented. Comet Churyumov-Gerasimenko, studied by the Rosetta mission, showed rotation period change of several minutes over months of activity, caused by reactive effect of gas ejections. But 3I Atlas's period change, if it truly occurred, was an order of magnitude larger, from 87 hours to just over 3. Such change required enormous torque, suggesting either catastrophic event during perihelion, fragment detachment, sharp outburst, or error in one of the measurements. On December 14th, a publication appeared in Astrophysical Journal Letters, a short article that underwent accelerated peer review due to topic relevance. A group from University of Maryland presented analysis of SOHO images obtained during 3I Atlas's perihelion passage. Using processing methods developed for studying solar corona, they isolated weak structures in the comet's tail, invisible on raw images. The structures resembled knots, local brightness condensations spaced about 500,000 kilometers apart. Knots in comet tails are regularly observed and explained by periodic material ejections from the nucleus. If a comet ejects dust in pulses rather than continuously, each pulse creates a clump that moves along the tail, gradually dispersing. Distance between knots is related to pulse period and material velocity. For 3I Atlas, 500,000 kilometers distance at dust velocity around 1 kilometer per second meant pulse period of about 6 days. This poorly corresponded to measured rotation periods. Neither 87 hours nor 3 hours 20 minutes yielded 6 days. If pulses aren't related to rotation, what causes them? Internal processes in the nucleus, subsurface layer heating, gas pressure accumulation, periodic crust breakthroughs, external influences, solar flares, solar wind plasma stream impacts. Each explanation required assumptions, and none was completely satisfactory. The paper's authors concluded cautiously, observed structures require further study and may indicate processes not accounted for in standard cometary activity models. On December 17th, the Cloudy Nights forum exploded with a new message. A user under the handle Lens Hunter posted an image obtained that same night using a 40-centimeter telescope in Arizona. The image showed 3I Atlas's coma, but with an unusual detail. To the side of central condensation, at distance of about 3 coma diameters, a second faint point was visible. The point's brightness was about 17th magnitude, 10 times dimmer than the main coma. The point wasn't a star. On the next frame, taken 40 minutes later, it shifted with the comet against the stellar background. A satellite? Nucleus fragment broken off during perihelion? Dust clump ejected by outburst and moving aside from the main tail? Or artifact, cosmic ray hitting the sensor during exposure, hot pixel, reflection inside the optical system? Lens Hunter claimed he checked. The point appeared on 3 consecutive frames, always in the same position relative to the coma moving with it. A cosmic ray or hot pixel wouldn't behave that way. This was a real object moving in 3I Atlas's vicinity. Several other observers attempted to confirm the finding. An observatory in New Zealand pointed a 24-inch telescope at the comet's coordinates the next night. Images were obtained, but the second point didn't appear. Either it became too dim, or changed position so it merged with the coma, or it never existed, and Lens Hunter's image was an artifact. Without independent confirmation, the observation remained in limbo. Intriguing, but unproven. On December 19th, 3I Atlas reached maximum approach to Earth for its entire stay in the solar system. 1.8 astronomical units, 270 million kilometers. Not close by human standards, but closer than it would ever be. After this moment, the object began steadily receding, increasing distance at about 3 million kilometers per day. Brightness fell accordingly, losing approximately 1/10 magnitude every 3 days. By end of December, the comet would dim to 13th magnitude, by end of January to 15th, by end of February, become accessible only to the largest professional telescopes. Time was running out, the window closing. Astronomers knew this and spent every clear night at instruments, accumulating final data before the object disappeared into inaccessibility. Each image, each spectrum, each measurement added pixels to the mosaic of understanding, incomplete, contradictory, but gradually forming. The question was whether they'd assemble enough details before the object left forever, or whether the truth about 3I Atlas would remain partially hidden, leaving room for speculation, theories, endless debates about what truly passed through the solar system in 2025. On December 23, 2025, 3I Atlas's brightness dropped to 12.6 magnitude, at the boundary between amateur and professional observations. The object was at 1.9 astronomical units from the Sun and continuing to recede, carrying away heat received during perihelion. The coma contracted to 120,000 kilometers, tail to 800,000. The comet was fading, returning to the dormant state that would persist for billions of years until it encountered another stellar system. Observers worldwide understood that each clear night might be the last opportunity to record details that would disappear when the object became too dim. Observatories in Chile, Australia, Hawaii worked at maximum capacity, accumulating exposures for several hours, summing signal, fighting noise. Professional astronomers obtained time on the largest instruments, 8-meter Gemini, Subaru, Very Large Telescope, for high-resolution spectroscopy, photometry, polarimetry. Each observation added a line to the database, another stroke to the portrait of an object that would soon vanish. On December 28th, a research group from University of California, Berkeley published a preprint analyzing polarization of light reflected by 3I Atlas's coma. Polarization, a light property related to electromagnetic oscillation orientation, changes when scattered by dust particles. From polarization degree and direction, dust particle size, shape, and composition can be determined. For 3I Atlas, polarization was unusually high, about 8% in red range, indicating either very fine particles, submicron size, or unusual grain shape, elongated, needle-like, possibly ice crystals. High polarization could be explained by sublimation processes. Water ice evaporating from the nucleus surface condensed in the coma, forming microscopic crystals that then gradually sublimated under solar radiation. Such crystals existed briefly, hours or days, but were constantly replenished with fresh material. This created a constant population of optimally sized particles for maximum polarization. Alternative explanation suggested 3I Atlas dust had different composition than solar system comet dust, possibly enriched with organic polymers or metallic inclusions, changing optical properties. On December 31st, the last day of the year, While most of humanity prepared for celebration, a small group of astronomers from European Southern Observatory spent the night at the VLT Telescope, Very Large Telescope, in Chile's Atacama Desert. Their goal was simple: obtain the last high-quality spectrum of 3I Atlas before the object became too dim. The 8-meter mirror, one of 4 in the VLT complex, collected photons for 4 hours, directing them to the UVES spectrograph, ultraviolet and visual Echelle spectrometer capable of separating light into tens of thousands of wavelengths with high precision. The result was obtained on the morning of January 1st, 2026, when sunlight flooded the desert and astronomers, having completed observations, were analyzing data in the control room. The spectrum showed what previous observations only hinted at: presence of complex organic molecules, cyanopyl-wines, carbon and nitrogen compounds rarely observed in comets, but building blocks for more complex organics. Sulfur-containing compound lines also appeared in the spectrum: hydrogen sulfide, sulfur dioxide, indicating a chemical environment possibly more reduced than in typical comets. The discovery of organic molecules in an interstellar comet was significant not only for understanding 3I Atlas, but for astrobiology as a whole. If interstellar objects transport organics between stellar systems, they could serve as vectors for spreading chemical precursors of life on galactic scale. Panspermia, the hypothesis of life spreading through space, received new supporting data, though remained far from proven. Presence of organics didn't mean presence of life, only chemical complexity. But this complexity was a step toward biology. On January 7th, 2026, 3I Atlas's brightness dropped below 13th magnitude, crossing the threshold beyond which the object became inaccessible to most amateur telescopes. Observations continued only in professional observatories, but session frequency declined. Time on large instruments is allocated months ahead among multiple projects, and the fading comet lost priority to other objects. Last images showed a faint spot against the starry sky, almost indistinguishable from galaxies of similar brightness, identifiable only by movement against fixed stars. On January 15th, another leak appeared, this time larger and more controversial. A 200-megabyte file was uploaded to several torrent trackers simultaneously, titled 3I Atlas EMRO Full Dataset Unverified. Contents included 112 images in FITS format, standard astronomical data format, allegedly obtained by the HiRISE camera on Mars Reconnaissance Orbiter during October 3rd observations. Each file contained metadata, timestamps, coordinates, instrument settings. At first glance, everything looked authentic, but expert verification revealed inconsistencies. File numbers didn't match the sequence used in official MRO archives. Some metadata contained values outside allowable ranges, detector temperatures above maximum operational, exposure times shorter than minimum. These could be copying errors, data corruption during transmission, or signs of fabrication. Several MRO mission specialists studied the files and gave contradictory conclusions. Some considered them high-quality fakes. Others allowed the possibility they were real data, damaged or modified during the leak. Among the 112 images, 10 showed the comet with sufficient resolution for distinguishing coma details. And on these 10 frames, with contrast enhancement and edge detection algorithms applied, structures emerged: concentric shells in the coma, radial rays, and in the center, in the maximum brightness area, hint of irregular source shape. Not a circle, not a point, but an elongated figure, possibly with angles. But resolution was at the limit. Each detail could be processing artifact, noise, desire to see what isn't there. The leak triggered a new wave of debates: forums, social media, science blogs, Everywhere discussed data authenticity and significance of what was seen. Some demanded official comment from NASA, confirmation or denial. The agency kept silent. On January 21st, a press secretary gave a brief statement. NASA does not comment on materials circulating in unofficial sources. Official publication of Mars Reconnaissance Orbiter data on Object 3I Atlas is scheduled for February 2026 in coordination with JUICE mission data. The date wasn't specified. February was approaching, carrying promise of answers, or at least new data. The JUICE probe completed observations on November 25th, accumulating gigabytes of information, images, spectra, infrared and ultraviolet measurements. Transmission began in December, slowly, byte by byte, through a communication channel several kilobits per second wide. By European Space Agency estimates, the full data array would be downloaded by mid-February. Processing would take another 2 weeks. Publication would occur in early March. Another month and a half of waiting. Meanwhile, 3I Atlas continued its journey away from the Sun. Late January found the object at 2.3 astronomical units from the star, receding at about 20 kilometers per second. Brightness dropped to 14.8 magnitude, requiring exposures of tens of minutes, even on the largest telescopes. The coma almost completely dispersed. Tail disappeared. The object became a point, practically indistinguishable from an asteroid, only its trajectory revealing interstellar origin, hyperbolic orbit heading to infinity. By mid-March 2026, the object would reach 16th magnitude. By June 18th, by year's end 20th. Each magnitude means brightness decrease by a factor of 2.5. 20th magnitude is the threshold for most Earth telescopes, except the largest operating in ideal conditions with long exposures. After this, 3I Atlas would become invisible to humanity, dissolve into cosmic abyss, carrying away mysteries, revealed, partially understood, and those that remained hidden. February 2026 began with silence. 3I Atlas was at 2.7 astronomical units from the Sun, continuing to recede at 19 kilometers per second, velocity that would never change until the object encountered another stellar system's gravitational field in millions of years. Brightness dropped to 15.4 magnitude, requiring hour-long exposures on professional instruments to obtain an image with sufficient signal-to-noise ratio. Observations became rare, once a week, then once every 2 weeks, as the astronomical community shifted to other targets, brighter, more accessible, more generous with data. But attention didn't fade completely. It moved from active observation to waiting for data from the JUICE probe, which according to European Space Agency schedule should be fully downloaded by mid-month. February 15th was a date marked on calendars of hundreds of specialists and thousands of enthusiasts worldwide. The date when silence should break, when accumulated gigabytes of information, 3 weeks of continuous observations after perihelion, when the object was most active, would become available for analysis. On February 7th, the European Space Agency published a brief note. Data download proceeding on schedule. 78% of the array already received, remaining 22% expected within a week. Processing would begin immediately after transmission completion. Publication of preliminary results scheduled for late February. Full data array would be available in archive by mid-March. Another 6 weeks from note publication to full availability. The astronomical community's patience was tested to its limits, but science has its own pace, not subject to desire for immediate answers. On February 10th, a new thread appeared on Reddit forum, created by a user with an account registered just hours earlier. Did anyone else notice the change in NASA's official position? The post contained comparison of two versions of the agency's press release published January 21st, original and modified. The difference was subtle but significant. In the original version available through Web Archive, it stated, "Publication of Mars Reconnaissance Orbiter data on Object 3I Atlas, scheduled for February 2026. In the modified version available on NASA's official website at post-publication time, the phrase read, "Publication of data will be coordinated with JUICE mission results and will occur no earlier than March 2026. No earlier than March. That's no longer February. Another delay, another month of waiting added without detailed explanation. Comments under the post quickly filled with speculation, from understanding the complexity of interagency coordination to suspicions of deliberate data concealment requiring additional verification or causing internal disagreements about how to interpret what was seen. Moderators didn't delete the post. Formally, it contained only comparison of official texts without adding unverified information. Discussion stretched to 240 pages in 24 hours. On February 14th, a group of independent researchers from the Netherlands Institute for Space Research published a paper analyzing all available data about 3I Atlas, both official and leaks, with caveat about the latter's unreliability. The 62-page paper contained systematization of anomalies, list of possible explanations for each, assessment of natural origin probability within known physics. The conclusion was cautious. The totality of 3I Atlas's observable characteristics finds no unambiguous explanation within existing cometary activity models. Either our understanding of processes occurring in interstellar comets is incomplete, or the object represents a new class of astronomical bodies requiring classification revision. New class of astronomical bodies. The wording was diplomatic, leaving room for interpretation. It didn't assert artificial origin, but didn't explicitly exclude it, placing it in the category of possibilities that couldn't be rejected without sufficient data. The article was published in peer-reviewed journal Astronomy and Astrophysics, meaning it passed expert evaluation and gave the conclusions weight, distinguishing them from social media speculation. Publication sparked response. Dozens of citations in other works, mentions in science blogs, author interviews in podcasts and popular science publications. On February 16th, the European Space Agency confirmed JUICE data download complete, processing begun. Preliminary results would be presented at a press conference on February 27th. 11 days until revelation. The agency gave no hints about results content, only confirmed observations were successful, data high quality, analysis in progress. Wording was neutral, professional, provoking neither enthusiasm nor alarm. But for those who'd followed the 3I Atlas story since discovery, 11 days seemed like eternity. During these days of waiting, 3I Atlas continued its journey, indifferent to human attention. Brightness dropped below 16th magnitude, making the object invisible to all except the largest observatories. The last amateur observation was recorded February 12th by an astronomer from Australia using a 45-centimeter telescope and 6-hour cumulative exposure. The image showed a barely distinguishable point at detection threshold, requiring careful processing to separate from background noise. This was a farewell glance, last opportunity for a non-professional to see the interstellar guest before its disappearance. On February 27th, at 10 a.m. Central European Time, a press conference took place at European Space Agency headquarters in Paris. The hall was filled with journalists, scientists, representatives of other space agencies. Online broadcast gathered over 200,000 simultaneous viewers, unusually high audience for a scientific event. Olivier Witas, JUICE project scientist, opened the presentation with brief mission overview and circumstances of 3I Atlas observations. Then the screen behind him filled with the first image. The comet in the image looked like a bright point surrounded by extensive, irregularly shaped coma. Color was artificial. Combination of several spectral ranges, colored to highlight details. Blue areas corresponded to water and hydroxyl emission, red to carbon dioxide and dust, green to organic compounds. Coma structure showed asymmetry, one side saturated with blue, the other red, as if two different ejection sources with different composition. Wittasi explained, such asymmetry could indicate nucleus composition, inhomogeneity, or multiple active areas ejecting material of different origin. Next slides showed spectra, graphs, tables. The infrared spectrometer recorded lines of water, carbon dioxide, methane, ammonia, cyanide, standard set. But lines were also present that sparked discussion in the analysis team. Weak but distinguishable signs of molecular nitrogen and carbon monoxide, substances that sublimate at very low temperatures and are rarely observed in comets because they evaporate long before the comet reaches inner regions of stellar systems. Their presence in 3I Atlas indicated either exceptionally cold object origin or that they were somehow protected from early sublimation, possibly sealed under a crust of less volatile substances. Wittasi continued, showing brightness time series measured over 3 weeks of observations. Brightness fluctuated with period around 3 hours 17 minutes, close to the period measured by Namibian observers in December. This confirmed nucleus rotation with this period, which was slow for a body this size, but not impossible. Fluctuation amplitude was about 12%, indicating surface inhomogeneity, areas with different reflectivity or shape, creating brightness change during rotation. But detail necessary for distinguishing nucleus shape was unattainable, even for JUICE instruments at such distance. The presentation's last slide contained brief summary. 3I Atlas is an active interstellar comet with unusual but not unprecedented chemical composition, showing signs of complex internal structure and inhomogeneous activity. The object represents exceptional interest for understanding planetary system formation processes in other parts of the galaxy and interstellar matter evolution. Further study requires closer observations, which could be achieved by the Comet interceptor mission scheduled for 2029, if another interstellar object can be detected and intercepted at early stage of passage through the solar system. The press conference lasted 1 hour 20 minutes, including questions. Not one mention of leaks, not a word about possibility of artificial origin, no dramatic revelations. Official position was clear. 3I Atlas is a natural object, interesting and unusual, but explainable within known physics, assuming some special formation and evolution conditions. For part of the audience, this was a satisfactory answer closing the question. For another part, this was the beginning of new questions, because absence of dramatic revelations didn't mean absence of anomalies, only their interpretation in the most conservative framework. Reaction to the press conference was predictably divided. For the scientific establishment, ESA's presentation provided exactly what was expected: thorough analysis, cautious conclusions, acknowledgement of the object's unusualness without extraordinary claims. For enthusiasts and those who'd followed the leaks for recent months, the official version seemed incomplete. Too much remained off-screen, too few explanations for accumulated anomalies. But this is classic tension between science requiring proof and curiosity craving immediate answers. On March 1st, 2026, the full JUICE data array was uploaded to the European Space Agency's public archive. Thousands of files, images, spectra, time series, metadata, became available for download to anyone with internet connection and software for working with astronomical data. During the first 24 hours, files were downloaded over 3,000 times from 217 countries. Independent researchers, students, enthusiasts began their own analysis, checking official presentation conclusions, seeking details that might have been missed or insufficiently emphasized. On March 5th, NASA fulfilled its long-standing promise and published the full Mars Reconnaissance Orbiter dataset. All 42 frames obtained October 3, 2025. Images showed 3I Atlas with promised resolution, but insufficient for distinguishing nucleus structure. The coma dominated, bright and extensive, hiding the central object beneath it. Photometric analysis confirmed coma size around 300,000 kilometers. Spectroscopy showed standard cometary gases. Nothing dramatic, nothing clearly contradicting natural origin. But in file metadata, several analysts discovered editing traces. Timestamps of some frames had microsecond discrepancies with observation logs available through other channels. Differences were negligible, fractions of seconds, and could be explained by technical peculiarities of clock synchronization between different systems. But they could also indicate post-processing, selective frame removal, data correction. Without access to original unprocessed files stored on Institute servers, verification was impossible. Suspicions remained. Suspicions, unprovable and irrefutable. Mid-March brought publication of a major review article in Nature Journal, a prestigious publication where the most significant scientific discoveries are published. The 8-page article, written by a consortium of 47 astronomers from 18 countries, summarized all 3I Atlas observations from discovery to February 2026. The conclusion was cautiously optimistic. The object demonstrates characteristics expanding understanding of interstellar body diversity, confirms existence of ancient comets formed in the early galaxy, and opens new directions for future research. The article became the canonical reference cited by subsequent works. By year's end, it would gather over 200 citations, an indicator of high influence in the scientific community. But it also became the point where the active research phase began transitioning to archival. 3I Atlas, by April, dimmed to 17th magnitude, by May to 18th. Observations became rare, once a month, then less. The object was receding, becoming fainter, attention shifting to other targets, more accessible, more generous with new data. On March 23, 2026, the comet passed at 5.2 astronomical units from Jupiter, far enough that the giant's gravity didn't noticeably change trajectory, but close enough that several astronomers proposed using the Juno probe for observations. Juno, operating in Jupiter's polar orbit since 2016, had instruments capable of capturing the comet if it appeared in field of view during one of the orbits around the planet. Observations were conducted March 29th. But results published in May showed only a faint point at detection threshold. The object was too dim and distant for detailed study. By June 2026, 3I Atlas was over 4 astronomical units from the Sun, receding at 18 kilometers per second. Brightness dropped to 19th magnitude, the threshold for all except the largest telescopes with multi-hour exposures. The last recorded observation by a professional observatory was dated June 27th, when the Hubble Telescope in Hawaii obtained an image showing a barely distinguishable point requiring complex processing to separate from starfield background noise. After this, 3I Atlas disappeared from human view. Not dramatically, not suddenly, simply dimmed below detection threshold, dissolved into countless faint points of distant space. By year's end, it would be at 6 astronomical units. By next year's end, 8. By decade's end, 15. Beyond Neptune's orbit, in the region where the solar system transitions to interstellar space. In 50 years, it would traverse 100 astronomical units. The boundary, only 2 human objects, the Voyagers, crossed in over 40 years of operation. In 10,000 years, 3I Atlas would leave the Oort cloud, enter true interstellar void, and travel millions of years until meeting another star. The story of 3I Atlas didn't end with publications and the object's disappearance from visibility. It continued in the form that all scientific mysteries without definitive resolution take: debates, data reanalysis, alternative interpretations. Preprints continued appearing on Archronium throughout the year, each offering a new model, new explanation for one or more anomalies. Some gained support, were published in peer-reviewed journals, became part of scientific consensus. Others were rejected, criticized, forgotten. The process slow, iterative, without dramatic revelations, but gradually forming understanding. Leaks didn't completely stop either. From time to time, new files appeared on anonymous forums, allegedly containing additional data, internal documents, correspondence between mission specialists. Most were quickly identified as fakes or rehashes of already known information. But several remained in limbo, neither proven nor refuted, existing in the gray zone between truth and fiction. Digital artifacts of an era when the line between official and anonymous, verified and dubious, blurred to near indistinguishability. By the end of 2026, interest in 3I Atlas shifted from active research to historical analysis. The object became an example in astronomy textbooks, a case for discussing methods of studying interstellar objects, a reference for planning future missions. Comet Interceptor, a European Space Agency mission scheduled for 2029, was designed with lessons from 3I Atlas in mind: necessity of rapid response to discovery, trajectory flexibility for intercepting objects with unexpected orbits, instruments for studying both coma and nucleus from close range. The question of what 3I Atlas truly was, an ancient comet from the early galaxy, a fragment of a destroyed world, or something else, remained without definitive answer. Science rarely gives definitive answers immediately. It accumulates data, builds models, tests hypotheses, gradually narrowing the area of uncertainty. For 3I Atlas, this area narrowed but didn't disappear. The object was studied sufficiently to exclude some extreme hypotheses, but insufficiently to answer all questions. And that's normal. That's how understanding the universe works. Step by step, object by object, discovery by discovery, approaching understanding, never reaching it completely, because each answer births new questions, and the journey continues infinitely, like the journey of 3I Atlas itself through the galaxy, begun billions of years ago and continuing now, at this very moment, when a dark point invisible to the human eye moves through the void, carrying away mysteries that perhaps will remain forever unknown. By autumn 2026, 3I Atlas disappeared from active scientific discourse, but not from memory. The object became a reference, starting point for everything concerning interstellar visitors. Every new paper about comets, every discussion of detection methods for small bodies beyond the solar system inevitably contained mention, as demonstrated by 3I Atlas, or unlike the case with 3I Atlas. The object took its place in scientific taxonomy, not just the third interstellar comet, but a standard of complexity, a set of characteristics against which all subsequent discoveries were measured. November 2026 brought publication of memoirs by one Space Telescope Science Institute technician who retired after 32 years working with Hubble data. The book was titled Light from Afar: 3 Decades of Space Discoveries, and mainly contained personal recollections of significant observations, technical problems, human stories behind dry scientific reports. But one chapter, titled The Comet We Couldn't Publish, attracted broad audience attention. In it, the author, without naming names and avoiding specific details, described the atmosphere at the Institute during processing of July 3rd Atlas observations. According to him, the images provoked unusual reaction from senior specialists. Not alarm, but caution. Need to recheck everything multiple times before publication. The decision to extend the proprietary period wasn't imposed from above, but came from the research group itself, wanting to ensure observed features weren't instrument artifacts or processing errors. The author wrote, "In science, there are things more frightening than missing a discovery, announcing a discovery that turns out to be an error. Reputation is built over decades and destroyed by one incorrect publication." The chapter contained no revelations about what exactly was in the images, but its tone, mixture of caution and understatement, fueled interest. December 2026 was remembered for the American Astronomical Society Conference, where an entire section was dedicated to interstellar objects. Over 20 presentations discussed Oumuamua, Borisov, and 3I Atlas, trajectories, composition, origin, future study strategies. Professor Avi Loeb delivered a plenary talk titled "When the Unusual Becomes Normal: Revising Criteria for Extraordinariness." He didn't assert artificial origin for any objects, but called on the community not to reject the hypothesis a priori, but treat it as one of many, testable by observations. The talk sparked heated discussion, lasting 2 hours without reaching consensus, which is normal for science at the cutting edge. By the end of 2026, the last recorded observation of 3I Atlas was dated October 8th. The Keck telescope in Hawaii obtained a spectrum of the object, already at 20th magnitude. The spectrum was weak, noisy, requiring 12-hour exposure, but it existed. Final testimony of coma chemical composition before final activity fade-out. Water and carbon dioxide lines were barely distinguishable. The object transitioning to inert state, freezing in cosmic cold, ceasing evaporation. After this, 3I Atlas became too dim even for the largest instruments. Theoretically, it could continue being tracked by digital stacking method, summing hundreds of images accumulated over months, isolating the moving point from static stellar background. But observatory resources are limited, telescope time distributed among thousands of projects, and continuing observations of an object providing no new information was economically and scientifically unjustified. 3I Atlas transitioned to the category of known but unobserved objects, bodies whose trajectories are calculated, but position isn't actively tracked. 2027 began with launch of new sky survey programs developed with 3I Atlas experience in mind. The Atlas system that discovered the object received funding for expansion. 4 new telescopes in the southern hemisphere, machine learning algorithms for automatic detection of fast-moving objects, protocols for immediate notification of the astronomical community upon detecting potential interstellar visitors. The goal was clear. Don't miss the next object. Detect it as early as possible while it's still far away, and there's time to organize observations. Summer 2028 saw the European Space Agency confirm final design of the Comet interceptor mission. The spacecraft, consisting of 3 modules, would be launched with another mission in 2029 and take position at the Earth-Sun system's Lagrange point L2, where it would await detection of a suitable target, preferably an interstellar comet or Oort cloud object entering the inner solar system for the first time. Upon target detection, the craft would leave its waiting position, head for intercept, separate into 3 modules for simultaneous study of the object from different angles and distances. Mission design incorporated all lessons from 3I Atlas, necessity of studying not only coma but nucleus, instruments for spectroscopy across wide wavelength range, high-resolution cameras for distinguishing surface structure, magnetometers for measuring solar-wind interaction, dust detectors for analyzing ejected particle composition. Everything lacking during 3I Atlas observations from millions of kilometers away. Comet interceptors should provide by approaching to hundreds of kilometers, possibly closer. 2029, the launch date, was still distant, but preparation was underway. Engineers designed systems, scientists determined priority measurements. The team developed operation scenarios for different target types. Mission success depended not only on technology, but on luck. Interstellar objects appear in the solar system rarely, perhaps once every few years, and there's no guarantee a suitable target would be discovered within the craft's opportunity window. But the attempt was worth it. A chance to study matter from another stellar system up close, solve mysteries that remained unresolved after 3I Atlas. Meanwhile, 3I Atlas itself continued its journey, invisible, forgotten by the general public, but not vanished. Trajectory was calculated with high precision. The object crossed Neptune's orbit in 2030, would reach 50 astronomical units, Kuiper belt boundary, by 2035, 100 astronomical units by 2060. Each milestone would be unnoticed, unmarked by observations, because the object long ago became too dim. But numbers exist in databases. Ephemerides update automatically, and in theory, if someone wished, exact position of 3I Atlas could be calculated at any future moment. In 10,000 years, the comet would leave the Oort cloud, crossing the solar system's gravitational boundary. In 50,000 years, it would be at 1 parsec distance from the Sun, 3.26 light-years, the distance to nearest stars. In 1,000,000 years, it might fly past another star, enter another planetary system, become a guest for another civilization, if such exists, or remain in interstellar void forever, one of countless bodies drifting in darkness between luminaries, a witness to the galaxy, a time capsule preserving in its depths matter from 7 billion years ago. The story of 3I Atlas ended not with revelation, but gradual fading of interest, transition from active research to archives. This is the story of most scientific mysteries. Not all are resolved by dramatic discovery. Many simply become background, context for next questions. The object left a trace in literature. Hundreds of papers, thousands of citations, place in future textbooks. It changed approaches to sky monitoring, stimulated development of new missions, expanded understanding of interstellar body diversity, and it left questions, not all, but some, without definitive answers, which is normal, because knowledge is infinite, and each generation of researchers continues where the previous stopped, adding new details to the mosaic of understanding, approaching truth asymptotically, never reaching it completely, but finding in the process itself meaning that doesn't require an endpoint, only forward movement into the darkness of the unknown, where perhaps new guests from the interstellar abyss await. Spring 2029 brought an event the astronomical community had awaited nearly 4 years: launch of the Comet interceptor mission. On April 27th, an Ariane 6 launch vehicle rose from the Kourou spaceport in French Guiana, carrying not 1 but 3 spacecraft assembled in a single configuration. The main module, built by the European Space Agency, and 2 smaller probes, one Japanese, the other European, designed for simultaneous study of the target from different viewpoints. The mission was unusual. It had no predetermined target, only a promise to wait. The trajectory brought the craft to Lagrange point L2 of the Earth-Sun system, located 1.5 million kilometers from Earth in the direction away from the Sun. This is a point of gravitational equilibrium where Earth's and the Sun's attraction balance centrifugal force, allowing a spacecraft to remain relatively stationary with minimal fuel expenditure. Other missions already operated here: the James Webb Telescope, Gaia Observatory, Euclid Probe. Now Comet Interceptor joined them, taking a waiting position that could last years. The task was unprecedented: detect a comet entering the inner solar system for the first time in millions of years, or, less likely but more exciting, an interstellar object passing close enough for intercept. Reaction time was critical. From target detection to approach could be just months, requiring quick decisions, trajectory calculations, engine ignition. Comet Interceptor was designed for such flexibility: autonomous navigation systems, powerful engines capable of providing velocity change up to 500 meters per second, sufficient for intercepting most potential targets. By summer 2029, a new generation of survey telescopes reached full operational readiness. The Vera Rubin Observatory in Chile, which began work in 2025, conducted the legacy survey of space and time, photographing all visible sky every 3 nights with unprecedented depth and precision. Each night, the system registered millions of objects. Machine learning algorithms isolated moving points, classified them: asteroids, comets, trans-Neptunian objects, artificial satellites. And among this data stream, they searched for special trajectories, hyperbolic orbits indicating interstellar origin. Statistics were unforgiving. Interstellar objects visit the solar system rarely. Oumuamua in 2017, Borisov in 2019, 3I Atlas in 2025, 3 objects in 8 years. If the pace continues, the next might appear in 2 to 3 years, or in 10, or never during the mission's lifetime. Probability that Comet Interceptor would detect a reachable interstellar object during a 5-year waiting window was estimated at 5 to 10%. Small chance, but non-zero, and this made waiting meaningful. More likely target was a long-period comet from the Oort cloud, a reservoir of trillions of icy bodies at distances from 10,000 to 100,000 astronomical units from the Sun. From time to time, gravitational perturbations from passing stars or galactic tidal forces eject one of these bodies onto an orbit leading to the Sun. The journey takes millions of years, and when the comet finally reaches inner regions, it's its first and possibly last visit. Such a comet's surface preserves pristine composition, unchanged by multiple heatings, a time capsule from the solar system's formation, era 4.5 billion years ago. The Vera Rubin Observatory discovered several long-period comets each month, most too far or on unsuitable trajectories for intercept. Target selection criteria for Comet Interceptor were strict. Comet must be detected at over 2 astronomical units from the Sun, allowing time for mission planning. Trajectory must permit intercept with available fuel reserve. Orbital period must exceed 10,000 years, preferably 1,000,000 or infinity, indicating first visit to inner system. Each month, the mission team reviewed new candidates, conducted preliminary calculations, but so far, none matched all criteria perfectly. Meanwhile, memory of 3I Atlas slowly transitioned from active to historical. 5 years after the object's disappearance from visibility, sufficient time for enthusiasm to cool, for speculation to quiet, for only what can remain to persist: scientific papers, data in archives, textbook mentions. Young astronomers beginning careers in the late 20s perceived 3I Atlas as a story told by senior colleagues, interesting, important, but belonging to the past, not their time. Each generation has its discoveries, and the next interstellar body would belong to them. Autumn 2030 brought an event that momentarily returned 3I Atlas to headlines. An independent researcher analyzing Hubble Telescope archival data discovered an unaccounted observation series conducted in July 2025. Additional frames not included in official publications. Files were found through automatic metadata search and proved technically valid, containing the same timestamps and parameters as known observations, but showing the object from a different angle. Images were processed and published on the researcher's blog. The frames showed what other observations only hinted at: coma asymmetry, structuring that could be interpreted differently depending on observer bias. For some, this was confirmation of natural cometary activity in homogeneity. For others, a hint at something unexplained. Discussion resumed for several weeks, articles in science blogs, social media posts, but without new data, it quickly dried up. The object was too distant, too dim to verify anything by observations. The truth, if it existed, remained in the past. In those months of 2025 when 3I Atlas was bright and accessible. By early 2031, Comet Interceptor had spent nearly 2 years at its waiting position. Systems functioned normally, fuel remained untouched. The Earth team checked status weekly, updated software, prepared for the moment that might come tomorrow or never. Waiting was part of the mission, planned and accepted, but psychologically, it created tension. Hundreds of people working on the project knew success depended not only on technology and planning, but on luck, on whether a suitable target would appear at the right time in the right place. Somewhere in space, far beyond Neptune's orbit, 3I Atlas continued its journey. By 2030, the object was at about 8 astronomical units from the Sun, invisible, inert, a frozen chunk of matter from another stellar system, carrying within itself information about the galaxy from 7 billion years ago. No one observed it, no one thought of it daily, but trajectory existed in databases, ephemerides updated, and theoretically, if someone wished, exact object position could be calculated at any moment. The comet became a number, coordinate, catalog entry, the fate of most astronomical discoveries after active study completion. The story of 3I Atlas had no clear ending, because such stories never end completely. They fade, transition from active to archival memory, become context for future discoveries. The object left a trace, in science, in data, in methods, in questions that continued being asked, even when the object itself disappeared into inaccessibility. And this trace will exist as long as human curiosity exists, as long as astronomers look at the sky, as long as each new generation asks the same eternal questions. What's there, beyond our world? What do wanderers from interstellar darkness carry with them? Are we alone in the universe? And if not, what messages does the cosmos write on the surfaces of objects that cross the abyss between stars, carrying within themselves memory of places and times we can only dream about? 3032 found humanity on the threshold of changes in the space program, but 3I Atlas was no longer part of current discussions. The object was far beyond Pluto's orbit, at about 50 astronomical units from the Sun, 7.5 billion kilometers, a number that ceases to have intuitive meaning, becomes abstraction. Light from the Sun reached this point in 7 hours, weakened to brightness 2,500 times less than on Earth. In such light, the comet was invisible, inert, frozen at temperature around 40 Kelvin, minus 233 degrees Celsius. But numerical existence continued. Ephemerides updated automatically in minor planet center databases, NASA JPL Horizons, European and Asian astronomical archives. Every day, algorithms recalculated the object's position, accounting for planetary gravity, relativistic effects, even solar radiation pressure. Though at such distance it was negligible, trajectory was known with precision to several kilometers for decades ahead. 3I Atlas became a mathematical entity, coordinate in space that no one observed but all could calculate. By this time, Comet Interceptor had spent over 3 years at L2 waiting position. The mission reviewed 17 potential targets, long-period comets discovered by observatories on Earth and in space. 3 matched reachability criteria, but the mission team rejected them for various reasons. 1 was too active. Risk of collision with dense coma exceeded acceptable. Another moved too fast, requiring velocity change exceeding fuel reserve. The third proved not a first visit to inner system, but an object with period around 8,000 years, making it less priority. No interstellar object appeared. Statistics were unforgiving. 3 objects in 8 years between 2017 and 2025. Then silence. Perhaps the pace was anomalously high in those years. Perhaps the next object would appear tomorrow. Perhaps in 10 years. Prediction was impossible. Interstellar visitors don't follow schedules. The mission continued waiting, but in European Space Agency corridors, discussions began about a backup plan. If a suitable target wasn't discovered by 2034, the mission would head to a pre-selected short-period comet, less scientifically interesting, but ensuring at least some result. Meanwhile, the generation of astronomers who began careers during 3I Atlas's passage reached maturity. They became professors, research group leaders, textbook authors in which the interstellar comet occupied an honored place in the chapter on solar system, small bodies, and surroundings. For their students, 3I Atlas was history told from screens and pages, an object of study, but not experience. Each generation separates from the previous, not so much by time as by experience. Those who observed the comet through telescopes, followed leaks, awaited publications, had connection with the object that those who learned about it from archives didn't have. Autumn 3033 saw a small group of enthusiasts organize a virtual conference dedicated to the 8th anniversary of 3I Atlas's perihelion. The event gathered about 300 participants, amateur astronomers, retired professionals, students interested in astronomy history. Presentations covered various aspects: archival data analysis, image reprocessing with modern algorithms, discussion of what was missed in initial research. One presenter showed results of applying neural networks to coma images, trained on data from thousands of other comets. The network isolated patterns human eye might not notice, subtle correlations in brightness distribution, hints at structure. But interpretation remained open. Patterns could be real physical structures or algorithm artifacts, seeing correlations in noise. Without new observations, verification was impossible, and new observations were impossible. The object long ago passed beyond visibility. The conference concluded without revolutionary discoveries, but with a sense that 3I Atlas's story wasn't fully written yet, that future generations with better instruments and methods would return to archival data and perhaps see what contemporaries missed. Somewhere in NASA archives, European Space Agency, Japanese JAXA, terabytes of unprocessed data were stored: raw telescope files, intermediate analysis results, internal reports, correspondence between specialists. Most was never published, considered technical, not representing scientific value. But in these files, perhaps details hid that would someday prove significant. When new theory appeared requiring verification on old data, when another object with similar characteristics was discovered, when context changed so that the past acquired new meaning, 3I Atlas by 3035 crossed the boundary of 100 astronomical units from the Sun, symbolic threshold beyond which the star's influence becomes almost indistinguishable from interstellar background. Voyager 1, launched in 1977, reached this distance in 2012, after 35 years of flight. 3I Atlas covered the same distance in 10 years. Difference in initial velocity, difference between object born in another stellar system and accelerated by its gravity to interstellar speeds, and probe created by humanity barely escaping the Sun's gravitational well. At this distance, the sun's gravity still dominated. A slower moving body would return. But 3I Atlas moved fast, 18 kilometers per second relative to the sun, and this velocity was sufficient for escape. In 10,000 years, the comet would leave the Oort cloud definitively, enter true interstellar space where nearest star's gravity would be comparable to solar. Millions of years later, perhaps it would fly past another star, perhaps enter another planetary system, become guest for other observers, if they exist. The story of 3I Atlas ended not with revelation or oblivion, but something in between. Gradual transition from present to past, from observed to remembered, from mystery to legend. The object left trace in science, data, papers, methods, inspiration for future missions. It left trace in culture, mentions in books, documentaries, forum discussions where enthusiasts decades later continued debating what truly passed through the solar system in 2025. And it left trace in human imagination, reminder that the universe is larger, older, and stranger than we can comprehend, that between stars, travel objects carrying history of places and times we know only by indirect signs, by light that reached us through billions of years, by composition of matter formed under conditions that no longer exist. 50 years passed since 3I Atlas's discovery. The date, July 1st, 2075, was marked by a small group of enthusiasts who organized a virtual meeting broadcast through the planetary network connecting Earth, lunar colonies, and Martian settlements. Participants were few, about 150 people, most over 70 years old, those who remembered events firsthand, who observed the comet through telescopes, who followed leaks, who awaited publications. For the rest of humanity, 3I Atlas was a footnote in history, interesting but not defining, one of many objects that passed through the system over decades. By this time, the comet was at over 200 astronomical units from the sun, 30 billion kilometers, a number that lost connection with everyday reality. Light from the sun reached this point in 28 hours, weakened to the brightness of a star in night sky. The object's temperature equaled cosmic background temperature, 2.7 Kelvin, minus 270.4 degrees Celsius. All molecular motion ceased, matter frozen in absolute stillness, except one thing, the comet itself hurtling through void at 18 kilometers per second, velocity that wouldn't change for millions of years. The Comet Interceptor mission concluded in 2037, not encountering an interstellar object but successfully studying long-period comet C2035D1, arrived from the Oort cloud after millions of years of wandering. Data was revolutionary for understanding the solar system's primordial composition, but didn't answer questions about 3I Atlas. The object remained unique in its totality of anomalies, a reference without complete explanation. Subsequent interstellar visitors, 4I discovered in 2042, 5I in 2051, showed different characteristics, expanding diversity of known types, but not exactly repeating 3I Atlas's pattern. Archives continued storing data. Each decade brought new analysis methods, quantum image processing algorithms, neural networks trained on millions of astronomical objects, spectral techniques allowing information extraction from noise. Students wrote dissertations revisiting old observations, published papers titled Reanalysis of 3I Atlas Data Using. Some works confirmed previous conclusions, others proposed alternative interpretations, still others found details initially missed. The process had no completion. Each generation of researchers saw in data what their era's tools allowed seeing. Leaks that spawned so much controversy in 2025 and 2026, by mid-century, became historical artifacts, studied not so much for content as phenomenon, example of official science and public curiosity interaction in an era of digital transparency. Several sociology of science dissertations analyzed the phenomenon using 3I Atlas as case study. Were leaks genuine? Some probably yes, some definitely no, the rest forever remaining in gray zone of uncertainty. Did it matter? For science, minimally, official data was ultimately published. For culture, more, leaks created narrative parallel to official, and this narrative lived its own life. The question of 3I Atlas's nature never received definitive answer, because definitive answers are rare in science dealing with unique events. Consensus leaned toward natural origin, ancient comet from early galaxy, formed under conditions different from modern protoplanetary disk peripheries, carrying chemical and isotopic signatures of stellar system from 7 billion years ago. Anomalies were explained by combination of factors: unusual composition, complex internal structure, slow rotation, uneven activity. Each detail found possible explanation, though the totality required some assumptions. A minority continued holding alternative hypotheses. Professor Loeb, who lived to 98 and continued publishing, released in 2070 a memoir book, Interstellar Messages, Science at the Edge of Knowledge, where he devoted a chapter to 3I Atlas. His position hadn't changed. Artificial origin hypothesis not proven, but not definitively refuted, and science must remain open to possibilities that seem extraordinary as long as they're consistent with observations. The book became bestseller, sparked discussions, didn't change scientific consensus, but kept alive the spirit of curiosity, without which knowledge stagnates. Somewhere far beyond the heliopause, in space where the sun's influence is indistinguishable from other Milky Way stars' influence, 3I Atlas continued its journey. Coordinates updated automatically in databases, though no one checked them regularly. The object became number, trajectory, abstraction. Physically, it existed. 11 kilometers of matter, temperature 2.7 Kelvin, velocity 18 kilometers per second relative to local standard of rest. But human connection with it thinned to symbolic. Memory of time when the universe sent a guest and humanity looked, studied, argued, tried to understand. In 10,000 years, the comet would definitively cross the Oort cloud boundary, enter true interstellar space. In 50,000 years, it would be at 1 light-year distance from the Sun. In 1,000,000 years, it might fly past another star. Statistical calculations indicate about 30% probability of approach to stellar system at distance less than 10,000 astronomical units within the next 5 million years. If a civilization exists there, having reached technological level allowing space observation, they would see what humanity saw: dark body moving on hyperbolic trajectory, carrying within itself matter from another place, another time. Would they ask the same questions? Comet or artifact? Natural or artificial? Would they have leaks, debates, minority insisting on extraordinary hypotheses? Or would their science be different? Their methods developed enough to distinguish truth immediately? Impossible to know. Can only imagine. 3I Atlas as message, written not by intelligence but by time and chance, read by all who encounter it, interpreted through lens of their understanding, their technologies, their hopes and fears. Silent wanderer carrying not information but mystery, identical for all observers across millions of years and parsecs of space. The story of 3I Atlas ends here, at this moment when words end and the object continues existing beyond narrative. The comet doesn't know its history, what it meant to one species on one planet during several years of its history. It simply exists and moves, as it existed and moved billions of years before meeting the solar system, and will exist and move billions of years after. Eternal, indifferent, beautiful in its simplicity. Piece of rock and ice hurtling through void, witness to the galaxy. Time capsule, mystery without answer. And in this absence of answer lies not defeat but invitation to continue looking, continue asking, continue the journey of knowledge that, like the comet's own journey, has no end point, only direction, only forward movement into darkness where everything is possible, where every dark point in sky might be beginning of new story, and where humanity, small and curious, continues peering into the abyss, seeking answers, finding questions, and in this process becoming slightly closer to understanding the universe, which is larger, older, and more mysterious than any narrative we can compose about it.